In the vast expanse of our universe, there are phenomena so strange, so unnerving, that even the brightest minds of science cannot explain them. What if the laws of nature we trust are only a fraction of the truth? Imagine theories so disturbing, they challenge everything we think we know about reality. What if time isn't as linear as we believe? What if consciousness is not confined to our brains? For the next 3 hours, we'll explore these terrifying questions, the unsolved, the unknown, the unthinkable. So sit back, relax, and let's dive into the theories that may change everything you thought was possible. In the silence of space, where stars flicker in the endless dark, there lies an idea so unsettling that it forces us to question everything we know about our existence. Imagine, for a moment, that the universe we see, touch, and feel is not as solid as we believe. What if, in some remote corner of possibility, we are not truly living beings with a deep connection to a real world, but mere fleeting thoughts, mere brains generated by random fluctuations in the fabric of space and time? This idea, known as the Boltzmann brain theory, is not the kind of concept that fits neatly into our everyday understanding of life. It emerges from the deepest, most abstract reaches of theoretical physics, where the known laws of nature begin to stretch and bend in ways that are impossible to imagine, and yet strangely plausible. Picture this: a cold, empty cosmos, one so vast that the sheer size of it leaves the human mind reeling. There are stars that have burned for billions of years, and others that have long since faded into nothingness. Entire galaxies spin in an eternal ballet, their distant light reaching us only after traveling through the vast void for millions of years. But in this endless, dark expanse, the laws of physics do not always behave as we expect. In this boundless reality, one fundamental law, the second law of thermodynamics, tells us that things tend to move toward greater disorder, toward entropy. Over time, energy and matter disperse, breaking down into chaos. But this process is not always as simple as it seems. In the unmeasurable stretches of time and space, there's the potential for incredible randomness. Could such randomness, in the right circumstances, create something as complex as a conscious mind? A mind, fully aware of itself, even if it is not rooted in a real physical world, but instead arises from pure, spontaneous fluctuations in the void? This is where the Boltzmann brain theory takes us. It suggests that, given enough time and space, random quantum fluctuations could generate isolated, fully formed brains, complete with memories, thoughts, and experiences, for no reason other than statistical possibility. These brains would appear out of nowhere, with no bodies to anchor them, no physical environment to belong to. They would be nothing more than isolated bursts of consciousness, drifting aimlessly through the dark void, with the illusion of reality surrounding them. But what does this idea mean for our understanding of the universe? Could we, in fact, be nothing more than the fleeting thoughts of a Boltzmann brain, a cosmic fluke of nature? This is the fundamental question that haunts the theory, and the answer, as with most mysteries of the universe, is not easy to grasp. The concept of the Boltzmann brain has its origins in the work of Ludwig Boltzmann, a 19th-century Austrian physicist whose work on statistical mechanics laid the groundwork for much of modern thermodynamics. Boltzmann's contributions helped us understand how particles and energy interact on a microscopic scale. But in the grand scheme of the universe, the second law of thermodynamics, which Boltzmann's work helped explain, suggests that entropy, disorder, always increases over time. As entropy increases, systems become less ordered, more chaotic. This would seem to suggest that, over long enough periods of time, the universe should eventually degrade into a state of maximum entropy, where no energy or matter is left in any useful form. But what Boltzmann's work didn't account for was the possibility that, in the right conditions, randomness could give rise to highly ordered systems. like a brain, or even a conscious mind. Over time, this idea began to take on new dimensions. The expansion of the universe itself, along with the notion of a multiverse, the possibility that our universe is just one of many, each with its own laws of physics, opened up new possibilities for what might exist beyond our own physical reality. It is here that the Boltzmann brain theory emerged, a strange and unsettling hypothesis suggesting that in the infinite expanse of space and time, it is statistically possible for consciousness to appear out of nowhere without any physical context at all. This is not to say that scientists believe this is the most likely scenario. In fact, it is widely regarded as an absurd possibility, given our current understanding of how the universe works. And yet, the theory raises a critical question. How can we be certain that the world we experience is not just an illusion, a fleeting fluctuation in the cosmic void? Consider the implications of such a theory. If we were Boltzmann brains, it would mean that everything we know about the physical world, the stars, the planets, the very ground beneath our feet, could be nothing more than a vivid, fleeting thought conjured up by the randomness of quantum mechanics. The people we know, the places we've been, the experiences we've had, could all be fabricated memories, artificially generated within a disembodied brain. At first glance, this might seem like an absurd or nonsensical idea, but in the world of theoretical physics, where the boundaries of reality bend and twist in unexpected ways, such ideas can take on a strange sense of plausibility. It is, after all, difficult to fully comprehend the immense vastness of the universe and the staggering amounts of time involved. In a cosmos where trillions of stars and galaxies are born, live, and die, could it not be possible that, in some distant corner of space and time, a consciousness could arise from nothingness? The Boltzmann brain theory takes this idea a step further, suggesting that the entire universe, from the formation of galaxies to the emergence of life, might be a statistical anomaly, a fleeting blip in the cosmic timeline. But how would we even know if we were one of these transient brains? How could we verify our own existence if the very fabric of our reality were nothing more than an elaborate illusion? As perplexing as it may seem, some physicists argue that the Boltzmann brain hypothesis offers a unique challenge to our understanding of reality. If we live in a universe that is purely random, with no underlying purpose or design, then how can we be sure that our perceptions of the world are genuine? If consciousness can arise out of nothing, could it be that the universe we experience is not real at all, but merely a random pattern that our minds are trying to make sense of? But even if we entertain this possibility, it leads to an unsettling paradox. If we are merely random brains in a void, why would we have any memories, any sense of continuity, any idea that our lives have meaning? Wouldn't such a system be inherently unstable, incapable of maintaining the illusion of self-awareness for more than a fleeting moment? The truth is, we may never know. The Boltzmann brain theory, as radical and mind-bending as it may be, is ultimately an exploration of the limits of human understanding. It forces us to confront the nature of reality itself, to question whether the world around us is truly what it seems, or whether we are, perhaps, nothing more than the product of a cosmic accident, a single, isolated consciousness within an incomprehensibly vast, uncaring universe. As we continue to look to the stars, to peer into the far reaches of space, one thing is certain. The deeper we delve into the mysteries of existence, the more questions we uncover, and the fewer answers we seem to find. Are we truly here, or are we just the faintest flicker of thought in a universe governed by chance? The mystery remains, just as profound and unresolved as it ever was. And so, the question lingers in the air, unspoken but ever present. If we are not what we believe ourselves to be, then what, or who, are we, really? In the vast, silent expanse of space, where stars flicker in the endless darkness, There is an idea so unsettling it forces us to question everything we know about existence. Imagine that the universe we perceive, the world we experience with all its tangible elements, is not as solid as we believe. What if, instead of being truly alive in a real world, we are merely fleeting thoughts, Boltzmann brains, spontaneous conscious minds generated by random fluctuations in the fabric of space and time? This theory, born from the deepest realms of theoretical physics, arises from the idea that the universe's sheer size and randomness could, in the right circumstances, give rise to fully formed brains. These brains would have memories, thoughts, and experiences, yet no body, no physical world to anchor them. They would simply exist as isolated bursts of consciousness, drifting through the void, surrounded by the illusion of reality. The theory gets its name from Ludwig Boltzmann, an Austrian physicist who contributed to our understanding of statistical mechanics and thermodynamics. According to the second law of thermodynamics, entropy or disorder increases over time. In the infinite stretches of space and time, this disorder could lead to random events where highly ordered systems, like a conscious brain, emerge purely by chance. While scientists regard this theory as highly unlikely, it raises an unsettling question. Could we be nothing more than a random fluctuation in the cosmos, a fleeting thought with fabricated memories and experiences? If we were Boltzmann brains, our world, the stars, the planets, even the ground beneath our feet, could be nothing but an illusion, a vivid dream conjured by randomness. This idea challenges the very nature of reality and the reliability of our perceptions. In the vastness of the universe, could such a cosmic fluke be possible? And if so, how would we ever know? Ever? As the sun dips beneath the horizon, casting its long shadows over a world we know so intimately, a peculiar thought begins to take root. Is everything we see, hear, and touch merely a facade? Could the very reality we live in be nothing more than a sophisticated illusion, a simulation generated by some higher intelligence or advanced technology? It's a question that stretches the limits of imagination and reason, yet it's one that some of the brightest minds in science and philosophy can no longer dismiss as pure fantasy. The simulation hypothesis suggests that our entire universe, the galaxies, the stars, the Earth beneath our feet, could be nothing more than a vast computer program, a digital construct created by an intelligence far beyond our comprehension. It is a theory that questions the very fabric of our existence, suggesting that everything we experience, every event, every moment, might not be as it seems. In many ways, this idea is the modern evolution of age-old philosophical questions. What is real? How do we know that what we perceive with our senses is truly the truth? It echoes the musings of ancient philosophers who pondered the nature of reality, even though they had no concept of computers, artificial intelligence, or quantum mechanics. But in the 21st century, it is no longer confined to the realm of philosophy. Today, scientists, mathematicians, and technologists are grappling with it, attempting to understand whether the world we experience is truly the product of nature, or if it could instead be a product of design. It was in 2003 that philosopher Nick Bostrom at the University of Oxford put forth the now famous argument known as the simulation argument, which asks us to consider the possibility that we may be living in a simulation. Bostrom's reasoning is both simple and profound. If advanced civilizations are capable of creating realistic simulations of entire universes, then it's statistically likely that we are part of one of those simulations, rather than living in the base reality. In fact, if such simulations are common, then the number of simulated realities could far exceed the number of base realities. So, according to Bostrom, it might be far more probable that we are living in a simulation than in the real world. For those unfamiliar with the concept, The notion of a simulation can be difficult to grasp. Our daily lives seem so real, so tangible. We interact with people, we feel emotions, we experience time moving forward. The world appears concrete, unyielding. How could this all be fake? Yet, when we turn to the realms of technology, things start to look very different. Consider the virtual worlds of video games, where entire ecosystems, societies, and characters are brought to life, governed by algorithms and lines of code. These digital worlds, though simple in comparison to our own, function with an internal logic. They create an immersive experience, one that could, in theory, become indistinguishable from reality. Now, imagine a future civilization with technology so advanced it could create a simulation so detailed, so intricate, that every particle, every atom, behaves according to the laws of physics. A simulation in which conscious beings, just like us, live out their lives, unaware of their true nature. Could this be possible? Could we, too, be living inside such a vast, complex simulation, merely the product of a few billion lines of code written by a far superior intelligence? The idea, though unsettling, begins to find its roots in the increasing sophistication of our own technologies. The history of computing, stretching back to the early 20th century, provides some eerie glimpses into what may be possible in the future. The first true computers, such as those developed during the Second World War, were primitive machines compared to today's supercomputers. Yet, even in their infancy, they demonstrated a curious capacity for complexity. With the rise of artificial intelligence, machine learning, and quantum computing, the line between the physical and the digital world becomes increasingly blurred. The ability of machines to simulate reality has grown exponentially, and with it, the possibility that future civilizations may possess the power to simulate entire universes. The idea of a simulated reality has been explored in science fiction for decades, but it's not just a trope of popular culture. The implications of the simulation hypothesis have seeped into academic and scientific discourse, gaining traction among some of the most respected thinkers of our time. In 2016, renowned physicist Neil deGrasse Tyson acknowledged that it's possible we live in a simulation. In fact, Tyson argued, we have no way of proving we are not in one. With no evidence to suggest otherwise, the idea that our universe is an elaborate simulation cannot be ruled out. Yet, as with many scientific theories, the simulation hypothesis is not without its detractors. Many scholars dismiss the idea as pure speculation, pointing out that there is no direct evidence to support it. To some, it remains a theoretical fantasy, the stuff of sci-fi novels and movies like The Matrix. However, the fact that serious scientists entertain this hypothesis reflects just how far-reaching and profound it is. It forces us to confront a question that, until recently, might have seemed absurd. What if everything we know is a simulation? As we delve deeper into the theory, we begin to encounter some unsettling ideas. If we are indeed living in a simulation, does that mean we are nothing more than characters in an elaborate game, programmed to follow certain paths and behaviors? Are our thoughts, emotions, and actions predetermined, the result of algorithms designed to replicate consciousness? Or, more disturbingly, is it possible that the simulation is not perfect? That glitches in the system reveal moments of inconsistency, like the déjà vu we sometimes experience, or the odd synchronicities that seem to occur in our lives? What if, as some theorists propose, our universe is one of many simulations, and the real world exists outside of our understanding, beyond our perception? If so, then the boundaries of our reality are infinitely more complex than we could ever comprehend. Each simulation could have its own rules, its own set of conditions, and its own version of reality. The very notion of reality as we know it could be just one layer in an endless stack of digital worlds, each one created for a different purpose, a different experiment, or a different kind of existence. At the heart of the simulation hypothesis lies one simple yet profound idea. What if the entire universe, from the birth of stars to the development of life on Earth, is a form of digital engineering? One particularly disturbing implication of this theory is the question of whether or not we have free will. If we are living in a simulation, to what extent are we in control of our actions? Are our choices preordained by the programmers of this artificial reality? Or are we truly autonomous beings? The idea of predestination, where everything we do is part of a larger plan designed by an unseen force, is a troubling thought for many. It forces us to reconsider the nature of responsibility, morality, and even consciousness itself. As we reflect on the implications of the simulation hypothesis, it's easy to become lost in the abstract. But there are real-world consequences to this theory as well. For instance, how might the discovery of a simulation, if it were ever proven, affect society's sense of purpose? If the universe is just a computer program, what does that mean for the meaning of life, the purpose of existence? Would our understanding of the cosmos, of life, and of consciousness be forever altered? Perhaps the most unsettling aspect of the simulation hypothesis is the possibility that we may never know the truth. After all, if our reality is a simulation, the creators of that simulation could have designed it in such a way that we would never be able to detect the illusion. It's a paradox. How can we prove we're not in a simulation if the very laws of nature governing our world could be programmed to prevent such a discovery? And if we ever did begin to uncover evidence of the simulation, would that be part of the design? A clue left by the creators to make us question our reality? In the end, we are left with more questions than answers. The simulation hypothesis challenges our most fundamental beliefs about existence, reality, and consciousness. It forces us to confront the possibility that the universe, in all its vastness, might not be what we think it is. And while the theory remains speculative, it is one that continues to captivate the minds of scientists, philosophers, and ordinary people alike, all of whom are left to wonder, are we living in a simulation, or are we merely the product of some far more complex and mysterious reality? As we delve deeper into the implications of the simulation hypothesis, we are confronted with questions that challenge our most cherished assumptions about existence. If our universe is indeed a simulation, it raises a profound dilemma. What is the nature of the creators or programmers who designed this reality? Are they benevolent architects, indifferent engineers, or perhaps something altogether more incomprehensible? One possibility that emerges from this line of thought is that the creators of our simulation may exist at a level of reality so far beyond our own understanding that their motivations, if any, are entirely unfathomable. In this sense, we might be no more than sophisticated algorithms in a cosmic experiment, with the entirety of our experiences, from the rise and fall of civilizations to the quiet moments of introspection, programmed into the simulation with a purpose that we cannot hope to grasp. Perhaps we are part of an experiment designed to test certain principles of physics, human behavior, or even the emergence of consciousness itself. In this view, our lives, our joy, our suffering, our love, could be as much a part of a grand experiment as the particles that make up the atoms we are formed from. This concept, though deeply unsettling, forces us to confront the possibility that the universe is not an isolated entity, but a constructed environment, a sandbox, if you will, where the boundaries of reality are dictated by the rules written into the code of the simulation. Much like a video game world, the laws of physics, space, and time that govern our lives could be nothing more than a set of parameters imposed upon us by the simulation's architects. If this is true, then the concept of free will takes on a radically different meaning. If our actions are part of a predetermined set of choices, governed by a hidden algorithm, then what does it mean to be human? Are we truly autonomous beings? Or are we simply characters in a game whose paths have already been set? In such a scenario, the line between reality and illusion becomes increasingly blurred. If our universe is a simulation, then our understanding of what is real, the very things we take for granted, like the sensation of touch or the passage of time, might be entirely fabricated. Imagine the impact of such a revelation. If we were to discover that the very fabric of our existence is an artificial construct, how would we even begin to process that information? Would our lives lose meaning, knowing that we are not the product of organic evolution, but instead the creation of some advanced intelligence? Or would the realization of our true nature lead to a kind of liberation, freeing us from the constraints of a seemingly deterministic reality? In this light, the simulation hypothesis begins to raise a host of existential questions. If we are living in a simulation, does that change our understanding of morality and ethics? In a world where everything is programmed, where actions and consequences are determined by code, can we truly be held accountable for our behavior? Is there such a thing as right and wrong if the very fabric of our reality is nothing more than a digital construction? These are not easy questions to answer, and the answers we might come up with may reveal even more uncomfortable truths about the nature of existence. Moreover, if we are living in a simulation, what is the nature of death? In many video games, death is but a temporary setback, a brief moment of transition before the player can respawn and continue their journey. Could it be that, in a simulated reality, death is no different? Perhaps our consciousness is not truly extinguished but simply reset, only to emerge again in another iteration of the simulation, perhaps with no memory of what came before. If this were the case, would the fear of death still hold the same weight? Or would we view it as just another part of the game, a cycle of existence that is ultimately meaningless, since we could never truly die? As we explore the idea of a simulated reality, we are also forced to ask ourselves whether there are any limitations to the simulations that could be created. In a universe governed by digital code, is it possible to transcend the constraints of time and space? Could the programmers of this simulation have given us the ability to manipulate our surroundings, to bend the laws of physics to our will, much like the characters in a video game can alter the world around them? If so, how would we even recognize such power? Would it be possible for us to gain control over the simulation, to hack the code and manipulate the reality we inhabit? Or are we simply bound by the rules of the simulation, unable to alter the world in any meaningful way? One particularly intriguing thought that arises from the simulation hypothesis is the possibility of glitches in the system, moments when the code fails to execute perfectly, revealing cracks in the fabric of our reality. These glitches might manifest as inexplicable phenomena, like déjà vu, the occasional sense of reality bending, or strange coincidences that seem to defy logical explanation. Could these be evidence that the simulation is not flawless, that the creators have made errors in the programming, or that they are purposefully allowing us glimpses of the truth? Some theorists speculate that these glitches might be signs of an underlying code that governs the universe, a code that, if understood, could unlock the secrets of the simulation and perhaps even give us the power to control our reality. Yet, even as we entertain these possibilities, we are still left with the fundamental question: how can we know for sure that we are living in a simulation? The very nature of the hypothesis suggests that we might never be able to prove it. After all, if we are in a simulation, the creators could have designed it in such a way that we would never be able to detect any flaws or inconsistencies. In this sense, the question of whether or not we are living in a simulation might be inherently unanswerable. We could spend our entire lives searching for evidence, only to find that the very nature of the simulation prevents us from ever discovering the truth. This leaves us in a paradoxical position. We may never be able to definitively prove whether or not we are living in a simulation, but the mere fact that we are asking these questions speaks to the profound impact of the idea. The simulation hypothesis forces us to confront the limits of our knowledge, to reconsider what it means to be real, and to question the very nature of existence. It invites us to think beyond the confines of our everyday experience and to consider the possibility that everything we know, every star, every person, every feeling, could be part of an intricate, carefully crafted illusion. In the end, perhaps the true value of the simulation hypothesis lies not in whether it is true or false, but in the way it challenges us to think. It reminds us that reality, no matter how concrete it may seem, is ultimately a construct, one that can be shaped, bent, or even erased. And in that recognition, we may find the courage to live more fully, to embrace the mystery of existence, and to seek meaning not in the certainty of what we know, but in the boundless possibilities of what we have yet to discover. For in the grand scheme of things, whether or not we are living in a simulation may matter less than the fact that we are here, conscious, aware, and searching for the truth, whatever it may be. The mystery persists. Imagine standing at the edge of a cliff, your heart racing, the wind howling in your ears as you take a step into the abyss. In that moment, your mind races. What happens if I fall? What will I feel? How will it end? And yet, as the world blurs around you, a strange thought lingers at the back of your mind. What if I don't die at all? What if, in some unfathomable way, I am still alive, simply somewhere else, a parallel reality where I continue to exist, even after the unthinkable has happened? This is the strange, unsettling premise of quantum immortality, a theory that stretches the boundaries of reality as we understand it, proposing that death is not necessarily the end of consciousness. Instead, it suggests that our perception of death may be merely an illusion, a fleeting moment in the grand tapestry of the multiverse. Could it be that when we face death, we don't actually cease to exist? Could there be a version of us that continues to live on, somewhere in another branch of reality? The theory is rooted in the heart of quantum mechanics, the branch of physics that governs the behavior of particles at the smallest, most fundamental level of the universe. Quantum mechanics is a strange and mysterious realm, one where the rules of classical physics break down, and particles can exist in multiple states simultaneously, a phenomenon known as superposition. Particles can be in two places at once, or spin in multiple directions, until they are observed, at which point they collapse into one state or another. This fundamental randomness and uncertainty challenge everything we thought we knew about how the universe works. It is within this quantum realm that the idea of quantum immortality takes root, emerging from the interpretation of a strange concept known as the many worlds interpretation, MWI. Proposed by physicist Hugh Everett III in 1957, MWI suggests that every time a quantum event occurs, the universe splits into multiple realities. Each possibility, each outcome of a decision or action, is realized in a separate, parallel universe. In other words, every time we make a choice, a new universe is born, with one version of us following one path and another version following a different one. But what does this have to do with death? The theory of quantum immortality posits that when we encounter a life-threatening situation, there are multiple possible outcomes, some of which lead to survival and some of which lead to death. According to the many worlds interpretation, instead of our consciousness ceasing when we die, it branches into another universe where we survive. The version of us that dies is left behind, but we continue to live on in the version of reality where we did not perish. In this sense, death is not a definitive end. It's just a transition to a new reality where we continue to exist, unaffected by the death we experienced in another universe. It's a deeply unsettling thought. Could we be living our lives, blissfully unaware, while in parallel worlds, we are constantly dying, each time escaping into a new reality where we continue to exist? It's a concept that forces us to confront the very nature of consciousness and existence itself. If this theory is true, then death, in its conventional sense, may be a far more fluid, complex experience than we've ever imagined. The idea of quantum immortality hinges on a few critical assumptions about quantum mechanics. First, there is the idea of superposition, where a quantum system can exist in multiple states at once. Then, there's the concept of decoherence, where the universe, through its interaction with various systems, splits into different realities, one for each possible outcome. Together, these ideas create the framework for the many worlds interpretation, which suggests that every possible outcome is realized in its own universe. For example, imagine a simple scenario. You're crossing a busy street when suddenly a car swerves towards you. According to the many worlds interpretation, in one branch of reality, you are struck by the car and die. But in another branch, you manage to jump out of the way just in time, surviving without injury. In both realities, there is a version of you that experiences the event. But in the universe where you die, your consciousness is left behind. And in the universe where you survive, you continue on as if nothing happened. Imagine standing on the edge of a cliff, your heart racing, the wind howling in your ears as you take a step into the abyss. In that moment, your mind races. What happens if I fall? What will I feel? How will it end? And yet, as the world blurs around you, a strange thought lingers at the back of your mind. What if I don't die at all? What if, in some unfathomable way, I am still alive, simply somewhere else, a parallel reality where I continue to exist even after the unthinkable has happened? This is the strange, unsettling premise of quantum immortality, a theory that stretches the boundaries of reality as we understand it, proposing that death is not necessarily the end of consciousness. Instead, it suggests that our perception of death may be merely an illusion, a fleeting moment in the grand tapestry of the multiverse. Could it be that when we face death, we don't actually cease to exist? Could there be a version of us that continues to live on, somewhere, in another branch of reality? The theory is rooted in the heart of quantum mechanics, the branch of physics that governs the behavior of particles at the smallest, most fundamental level of the universe. Quantum mechanics is a strange and mysterious realm, one where the rules of classical physics break down and particles can exist in multiple states simultaneously, a phenomenon known as superposition. Particles can be in two places at once, or spin in multiple directions, until they are observed, at which point they collapse into one state or another. This fundamental randomness and uncertainty challenge everything we thought we knew about how the universe works. It is within this quantum realm that the idea of quantum immortality takes root, emerging from the interpretation of a strange concept known as the many worlds interpretation, MWI. Proposed by physicist Hugh Everett III in 1957, MWI suggests that every time a quantum event occurs, the universe splits into multiple realities. Each possibility, each outcome of a decision or action, is realized in a separate parallel universe. In other words, every time we make a choice, a new universe is born, with one version of us following one path and another version following a different one. But what does this have to do with death? The theory of quantum immortality posits that when we encounter a life-threatening situation, there are multiple possible outcomes, some of which lead to survival and some of which lead to death. According to the many worlds interpretation, Instead of our consciousness ceasing when we die, it branches into another universe where we survive. The version of us that dies is left behind, but we continue to live on in the version of reality where we did not perish. In this sense, death is not a definitive end. It's just a transition to a new reality where we continue to exist, unaffected by the death we experienced in another universe. It's a deeply unsettling thought. Could we be living our lives, blissfully unaware, while in parallel worlds, we are constantly dying, each time escaping into a new reality where we continue to exist? It's a concept that forces us to confront the very nature of consciousness and existence itself. If this theory is true, then death, in its conventional sense, may be a far more fluid, complex experience than we've ever imagined. The idea of quantum immortality hinges on a few critical assumptions about quantum mechanics. First, there is the idea of superposition, where a quantum system can exist in multiple states at once. Then, there's the concept of decoherence, where the universe, through its interaction with various systems, splits into different realities, one for each possible outcome. Together, these ideas create the framework for the many worlds interpretation, which suggests that every possible outcome is realized in its own universe. For example, imagine a simple scenario. You're crossing a busy street when suddenly a car swerves towards you. According to the many worlds interpretation, in one branch of reality, you are struck by the car and die. But in another branch, you manage to jump out of the way just in time, surviving without injury. In both realities, there is a version of you that experiences the event, but in the universe where you die, your consciousness is left behind, and in the universe where you survive, you continue on as if nothing happened. It's easy to see how this could lead to the idea of quantum immortality, the notion that as long as there are possible worlds in which you survive, you will continue to experience life, forever avoiding death. But there's a catch. You will never know you've died. Every time a version of you is killed, your consciousness simply shifts into the next universe where you are alive, with no memory of the death that just occurred. In this way, you become immortal, but only from your own perspective. From the perspective of the universes where you die, your story is over. But from your own point of view, you keep living. Now, this idea, though intriguing, is not without its critics. Many scientists dismiss the notion of quantum immortality as mere speculation, an interpretation of quantum mechanics that is far too abstract and unprovable. After all, there is no direct evidence of parallel universes or alternate realities in the way that the theory requires. Furthermore, the idea that consciousness could jump between realities is highly controversial. Our understanding of consciousness is still in its infancy, and the mechanisms by which we experience the world remain a mystery. Is it even possible for our subjective experience to transcend the boundaries of a single universe? Yet, despite the lack of empirical evidence, the idea of quantum immortality resonates with certain aspects of human experience. After all, we are all aware of the fragility of life. We face dangers daily, from the small, seemingly insignificant choices we make to the larger, life-threatening events that lurk on the horizon. And in those moments of uncertainty, many of us wonder, what would happen if I died today? Is there something beyond this life, or is the end truly the end? The concept of quantum immortality is also deeply connected to ideas about fate and free will. If death is not final, but instead a transition to another universe, does that mean our lives are predestined? Or does it simply mean that every possible outcome is realized, and we are unable to know which one we are in at any given time? In this sense, quantum immortality challenges our understanding of life and death, asking us to reconsider what it means to truly be alive, and whether we ever truly die at all. But even if we accept that quantum mechanics could, in theory, create a universe where death is not the end, we are still left with a deeper mystery. Why are we alive at all? If our consciousness is continually shifting between realities, always surviving, always continuing, what does that mean for our sense of self? Are we truly living, or are we simply a series of quantum fluctuations, bouncing from one universe to the next, with no true continuity of existence? The mystery deepens further when we consider the possibility that our experience of reality might not be as consistent as we believe. Could we, at this very moment, be in the middle of a quantum transition, unaware that the version of us that once existed in a different reality is now dead? Could it be that the only thing holding us together is the illusion of continuity, a story we tell ourselves to make sense of our lives? As we venture deeper into the unknown, we are left with more questions than answers. Quantum immortality forces us to confront the very nature of life, death, and consciousness itself. Is it possible that we are living in a vast, interconnected multiverse where death is simply an illusion? Or is this just another unprovable theory, a speculative idea that, like so many before it, challenges our understanding of the universe without providing any definitive answers? The enigma persists, as does the haunting question. What if we could never truly die? Could the very nature of existence be something far more complex and mysterious than we've ever imagined? As we turn our attention to the next mystery in our exploration, we are reminded that the answers we seek may be far beyond our reach, hidden within the folds of reality itself. And perhaps, just as with quantum immortality, some of these mysteries will remain unsolved, leaving us to wonder what else might be lurking in the shadows of the unknown. As you stand under the vast, star-strewn sky, the silence of the cosmos stretches out before you. The constellations blink like ancient beacons, and in the distance, planets orbit invisible stars, their orbits stretching for eons. It's easy to imagine that we are not alone. The universe, after all, is staggeringly immense, filled with billions of galaxies, each containing billions of stars, many of them likely with planets in the so-called habitable zone, where life, as we know it, could exist. Yet, despite the vastness of space, there's one thing that's oddly absent: any sign of intelligent extraterrestrial life. In fact, after decades of searching, not a single confirmed signal, message, or visit from an alien civilization has been detected. And this absence, this silence, is at the heart of one of the most perplexing and unsettling mysteries in science: the Fermi Paradox. Named after the renowned physicist Enrico Fermi, the paradox is deceptively simple. Given the vast number of stars and planets that are theoretically capable of supporting life, why then have we not yet encountered any evidence of extraterrestrial civilizations? Why, with all of the odds in their favor, are we still alone in the cosmos? It's a question that cuts to the core of our understanding of life, intelligence, and our place in the universe. The story begins in the 1950s, when Fermi, while having lunch with colleagues at the Los Alamos laboratory, posed a seemingly innocuous question: where is everybody? He was referring to the fact that, despite the likelihood of alien life being widespread in the galaxy, we had not yet encountered any signs of it. Given the sheer number of planets orbiting stars, some of which would likely be billions of years older than Earth, it seemed almost certain that civilizations more advanced than ours should have already made their presence known. And yet, as Fermi and his colleagues pondered, no one could provide a satisfactory answer. This simple question, delivered almost in passing, became the foundation for one of the greatest intellectual puzzles of modern science: the Fermi Paradox. The contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them has haunted scientists, philosophers, and thinkers for decades. In fact, it has only grown more perplexing as our technology has advanced, and yet, despite our most sophisticated efforts, the universe remains eerily silent. To understand the paradox fully, it helps to explore the reasoning behind Fermi's initial question. Statistically, the likelihood of other civilizations existing seems almost certain. Our Milky Way galaxy alone is home to an estimated 100 to 400 billion stars, many of which host planets within their habitable zones, the Goldilocks zones where conditions might be just right for liquid water and life to emerge. In recent years, the discovery of exoplanets has surged, with thousands of planets outside our solar system identified, many of them potentially Earth-like. So, if life is so probable in such vast numbers, why haven't we found any clear signs of intelligent life? Many explanations have been proposed over the years, some plausible, others more speculative, but none provide a definitive solution to the paradox. One of the most conventional explanations for the Fermi Paradox is the sheer scale of space itself. The distances between stars are staggering. Even the nearest star to our solar system, Proxima Centauri, is over 4.2 light-years away. This means that any signal from an alien civilization, even one sent at the speed of light, would take years or even centuries to reach us. In this context, it's easy to see how the vastness of space could contribute to the silence. Perhaps civilizations are simply too far away, and the vast distances prevent us from detecting their signals. But this explanation raises its own questions. If civilizations are so far apart, why haven't we picked up any signs of their existence, radio signals, light patterns, or other forms of communication, over the past century or more? After all, humans have been broadcasting radio waves and other electromagnetic signals since the early 20th century. Wouldn't it make sense that some other civilization might have detected these signals, just as we now detect signals from far-off stars? Another possible explanation for the Fermi Paradox is that Earth might be extraordinarily unique, a rare gem in the vastness of the universe. The rare Earth hypothesis suggests that the conditions necessary for the emergence of complex life may be so rare, so finely tuned, that Earth is an anomaly. According to this theory, while microbial life might be relatively common throughout the galaxy, the complex ecosystems and intelligent civilizations we are searching for could be exceedingly rare. Our planet's perfect distance from the Sun, the presence of a large moon that stabilizes our axial tilt, and the unique geological and climatic conditions all contribute to life as we know it. Other planets, though they might share some of these characteristics, may not have the precise conditions necessary to give rise to intelligent life. While this hypothesis seems to answer the question of why we haven't found anyone, it's far from universally accepted. Some argue that the universe is simply too vast and too old for complex life to be so rare. With billions of galaxies, each containing billions of stars, the sheer number of opportunities for life to develop seems overwhelming. Could Earth truly be the only planet where life has taken root? A more disturbing theory that has emerged in recent years is known as the Great Filter. According to this hypothesis, the universe may be teeming with life, but intelligent civilizations are extremely rare because there is some step, or series of steps, in the development of life that is extraordinarily difficult to overcome. This filter could exist at any point in the evolution of life, from the emergence of single-celled organisms to the development of complex, intelligent life forms. It's possible that intelligent civilizations are doomed to destroy themselves before they can establish long-lasting interstellar communication. In this context, the absence of alien civilizations might not be a sign of cosmic emptiness, but a tragic reflection of the fragility of intelligent life itself. For example, consider the many threats that could wipe out a civilization: nuclear war, climate change, pandemics, or even the collapse of ecosystems. Given that humanity has only been capable of advanced technology for a few hundred years, it's not hard to imagine that other civilizations may have self-destructed long before they had the chance to communicate across the stars. The great filter might therefore lie ahead of us. Perhaps the future of human civilization will be one of either great triumph or catastrophic failure. But if the great filter lies behind us, what could it be? Is there a step in our own evolution, some moment when life could have gone extinct, that was so improbable, so unlikely, that it has never been repeated elsewhere in the universe? One particularly intriguing, though highly speculative, idea is the zoo hypothesis, which proposes that extraterrestrial civilizations exist, but they are deliberately avoiding contact with us. According to this theory, advanced civilizations may view humanity much like we observe wildlife in a nature reserve or a zoo. We are simply too primitive, too dangerous, or too insignificant to interact with, and thus we are being left to evolve on our own, shielded from contact by some kind of cosmic prime directive. This hypothesis is unsettling in its implications. It suggests that, despite our sophisticated technology and curiosity, we may not be alone in the universe, but rather we are being deliberately ignored by more advanced civilizations. This notion raises questions about the ethics of contact. Would extraterrestrial civilizations choose not to interfere with our development? Would they allow us to progress naturally, without their guidance, perhaps to avoid altering our trajectory or causing harm? The zoo hypothesis also raises the issue of why, then, no signs have been observed. If extraterrestrials are deliberately avoiding us, why do we see nothing at all? Could it be that the zookeepers are so skilled at concealing their presence that not even the faintest trace of their existence reaches us? It's a haunting thought, that we might be part of some cosmic experiment, being watched from the shadows by those who have the power to shape our fate. In fact, it is not just the continuity of your self-awareness that comes into question. It's the very fabric of what it means to be alive. In the traditional sense, to be alive means to experience time in a linear fashion, to be born, to grow, to change, and ultimately to die. Yet, if quantum immortality is true, time itself might not be as linear as we perceive it. Time might not be a sequence of moments that move in one direction. Instead, it could be a vast web of parallel realities, each one existing simultaneously, with each version of you experiencing different events at the same time. This leaves us to question the very nature of time. Is it real, or is it just another layer of illusion that helps us make sense of our existence? Moreover, this theory raises profound ethical questions about our understanding of free will and responsibility. If every possible outcome of every decision is realized in some parallel universe, what does that say about our choices? Are we truly responsible for our actions if every possible outcome is played out somewhere in the multiverse? Or is our perception of free will just another illusion, a comforting narrative designed to help us navigate a universe where the lines between life, death, and destiny are impossibly blurred? The idea of quantum immortality also brings to light a fascinating connection between quantum mechanics and the nature of consciousness. In quantum theory, consciousness plays a pivotal role in collapsing the wave function, the process by which a quantum system moves from a state of probability to a definite state. In a sense, consciousness is the observer that shapes the universe, determining which reality manifests and which remains a potential possibility. If this is true, then the role of consciousness in shaping reality becomes far more complex than we ever imagined. Could it be that our very perception of death, the idea that we cease to exist, is simply the result of our consciousness collapsing into a reality where death is an impossibility, leaving behind the illusion of an end? While many of these questions remain speculative, it is clear that the idea of quantum immortality forces us to confront the limitations of our understanding of both physics and philosophy. It forces us to question the very essence of life and death, to explore the boundaries of reality itself, and to grapple with the idea that our experience of the universe may be far more complex and mysterious than we could ever comprehend. At the same time, the theory has an unsettling beauty. It suggests that death, that inevitable and defining feature of human existence, might not be an absolute end, but rather a moment of transformation, a shift from one reality to another. The prospect of infinite life, spread across infinite universes, offers a strange comfort. The idea that no matter what happens, no matter how dangerous the world around us becomes, there is always another version of us somewhere, still alive, still experiencing the world in a different way. This might be the ultimate form of immortality, not the endless continuation of a single consciousness, but the perpetual existence of countless versions of ourselves, each one living out its own unique reality. But then again, we are left with the haunting question: if we live forever, in one form or another, does life lose its meaning? If every possible outcome of our decisions is realized, then what does it matter what we choose? Is there value in living a life where death is not the final act, where every choice we make is simply one thread in an infinite tapestry of existence? Or does the very concept of immortality undermine the beauty of life, making each moment feel less precious, less significant? The idea of quantum immortality brings us to the edge of the known universe, where the rules of physics and philosophy collide. It suggests that death may not be the end at all, but merely a door leading to another version of reality, a version where we continue to live, perhaps unaware of the lives we've left behind. It forces us to confront the meaning of existence, to reconsider our perceptions of self, identity, and mortality, and to grapple with the terrifying yet fascinating possibility that we may never truly die, but simply live on, forever, in the shadows of infinite realities. In the end, whether or not quantum immortality is true, its exploration challenges us to think more deeply about what it means to be alive. It invites us to explore the nature of existence, to ponder the infinite possibilities that might lie hidden within the fabric of reality, and to question the very boundaries of life and death. And as we peer into the vast unknown, perhaps we come to understand that the greatest mystery is not whether we live forever, but what we choose to do with the time we have, in this universe or any other. The vast, endless expanse of space, intelligent civilizations may be in a constant state of fear and distrust, and the reason we have not detected any signs of extraterrestrial life could be due to the grim reality of the dark forest hypothesis. According to this theory, the universe, much like a dark forest, is a place where every civilization is a silent hunter, ever wary of the potential threat posed by others. In such a universe, the safest strategy for any civilization is to remain hidden, as revealing one's existence could invite annihilation. The concept behind the dark forest hypothesis draws from the logic of survival. If every civilization is unaware of the intentions of others, the safest course is to assume that every other civilization is a potential threat. The metaphor of the dark forest captures this chilling scenario perfectly. If you are in a dark forest, and you don't know who or what is lurking in the shadows, it's better to stay silent and hidden rather than risk making your presence known. In this way, advanced civilizations may avoid making contact, choosing instead to live in isolation, quietly concealing themselves for fear of being destroyed by an unknown adversary. This theory highlights the inherent dangers of interstellar communication, especially in a universe where advanced technologies could easily enable one civilization to destroy another. If civilizations are aware of the potentially catastrophic consequences of revealing their existence, they may choose to remain completely silent, deliberately avoiding all forms of detectable signals, from radio waves to any other observable phenomena that might give their location away. Thus, we might be living in a universe filled with countless intelligent beings, each one too afraid to make contact, and each one remaining isolated in their own corner of space. The idea that intelligent life might be deliberately hiding from us adds another layer of complexity to the Fermi Paradox. It's not that extraterrestrials are absent, but that they are actively avoiding us. However, while the dark forest hypothesis paints a sobering picture of the cosmos, it also raises deep questions about the nature of intelligence itself. If this theory is correct, it implies that the very drive for survival, the need to protect oneself and one's civilization at all costs, might be a universal characteristic of all intelligent life. It suggests that, as civilizations become more advanced, they also become more self-preserving, which could lead to an increasing reluctance to engage with others, especially when the stakes are as high as intergalactic survival. In this sense, the paradox is not just a question of why we haven't heard from extraterrestrials, but a reflection of the fundamental nature of intelligence, that the more we learn and evolve, the more we might become aware of the risks involved in making contact with others. But could this theory extend beyond our understanding of extraterrestrial civilizations to our own? Could it be that, as we develop more advanced technologies, such as artificial intelligence and space exploration, we too might face a moment where we must decide whether or not to make our presence known to the universe? If we are not careful, we could find ourselves in a situation where the very survival of humanity depends on remaining hidden from more advanced civilizations, much like the silent creatures of the dark forest. Perhaps the question isn't just why we haven't found extraterrestrial civilizations, but also whether we, as a species, should ever attempt to reach out to the stars. Should we, like those advanced civilizations in the dark forest, remain quiet and hidden for fear of the unknown consequences of contact? While the dark forest hypothesis posits a universe full of fear-driven isolation, it also presents a sobering realization about the future of space exploration. The more we look outward into the cosmos, the more we begin to understand the risks that come with making ourselves visible. As we develop the technology to detect distant stars and planets, we also develop the capacity to send out signals into the void. This potential for interstellar communication raises important ethical questions. Should we actively search for alien civilizations, or should we proceed with caution, aware that we may be exposing ourselves to existential threats? The increasing reality of our own technological development means that the risks of making ourselves known to the universe are no longer hypothetical. They are a tangible, looming possibility. Despite the unsettling implications of the dark forest hypothesis, it's not the only theory that seeks to explain the silence of the cosmos. One more optimistic possibility is that we have simply not yet been looking in the right way, or that the methods we use to search for extraterrestrial life are flawed. The search for extraterrestrial intelligence, SETI, for example, has been focused primarily on detecting radio signals or electromagnetic waves that might indicate the presence of alien civilizations. However, these methods may not be sufficient to detect more advanced forms of communication. Perhaps extraterrestrial civilizations are using technologies far beyond our current capabilities to detect or communicate. In this case, the silence we experience might not be the result of extraterrestrials avoiding us, but rather because we have not yet discovered the correct methods or technologies to identify their signals. This argument posits that the absence of detectable alien civilizations is not evidence of their absence, but rather a result of our limited understanding of the universe. Just as our ancestors once believed the Earth was the center of the universe, we may still be operating under the assumption that aliens would communicate in the same ways we do, using technologies we understand. But as our understanding of physics, communication, and even consciousness continues to evolve, it's entirely possible that the methods we use to search for extraterrestrial life are simply too primitive to detect the presence of civilizations far more advanced than our own. This leads us to another potential solution to the Fermi Paradox, the possibility that we may be experiencing a cosmic blind spot. Our methods of searching for alien life are all based on assumptions about how advanced technologies would manifest in the observable universe. But what if intelligent life exists in forms that are completely different from what we can imagine? Perhaps aliens are not using radio waves or electromagnetic signals at all. Perhaps they communicate using forms of energy or matter that we cannot yet detect. Or perhaps they exist in ways that transcend the physical dimensions we can perceive. If this is the case, then the silence of the universe may not be the absence of life, but simply our inability to perceive it. Another intriguing possibility that falls in line with this idea is the concept of a post-biological civilization, one that has evolved beyond the need for physical bodies. Such a civilization could, theoretically, exist in a purely digital form, inhabiting a virtual or artificial environment. As our own technologies advance, we are increasingly creating virtual realities and artificial environments that can simulate consciousness and life in ways that would have been unimaginable only a few decades ago. What if, in the far future, a civilization manages to upload its consciousness into a digital realm, no longer relying on the physical world for survival? Such a post-biological civilization might be entirely undetectable by our current methods, leading us to believe that the universe is empty when in fact it is full of life, just life that exists beyond our understanding of biology and the physical world. The silence of the cosmos, the haunting absence of extraterrestrial signals and evidence of intelligent life, continues to provoke deep reflection on our place in the universe. The Fermi Paradox is not just a question of where the aliens are, it's a question about the nature of life, intelligence, and existence itself. Could it be that the universe is teeming with life, but that life exists in forms so vastly different from our own that we simply cannot recognize it? Or could it be that the universe is quiet because civilizations are self-destructive, hiding from one another, or avoiding us altogether for reasons we cannot yet fathom? The mystery of the Fermi Paradox challenges us to expand our thinking, to push the boundaries of our understanding, and to confront the possibility that we are both profoundly insignificant in the grand scale of the cosmos and yet uniquely positioned to ask these very questions. In the end, perhaps the silence is not so much a void, but a reminder of how little we truly know and how much there is still to discover. Imagine, for a moment, that you are standing alone in a vast, dense forest, its trees towering above you, their branches thick with leaves that blot out the sky. The air is still, almost suffocating in its quiet. As you step deeper into the shadows, you begin to realize something unsettling. The forest is not empty. Somewhere, hidden just out of sight, other beings are moving, waiting, observing. You feel the weight of their gaze, not because they want to welcome you, but because they are just as afraid of you as you are of them. The forest is silent, deadly silent. No one dares to speak, for fear of revealing their position. Every movement, every sound, could be the last. You don't know who or what is out there, but you know this: there is only one rule in this forest: survive. This is the essence of the dark forest theory, a chilling hypothesis that offers an explanation for the Fermi Paradox. Why, despite the vastness of the universe, we have not yet encountered any signs of extraterrestrial life. The theory, proposed by Chinese science fiction author Liu Cixin in his novel The Three-Body Problem, suggests that the universe is akin to a dark, cosmic forest, filled with intelligent civilizations that, like hunters, are terrified of revealing their presence. The central tenet of the dark forest theory is simple. In a universe where survival is paramount, silence is the only way to ensure your safety. As we ponder the Fermi Paradox, why we haven't detected any alien civilizations, despite the overwhelming statistical likelihood of their existence, the dark forest theory presents a grim and unsettling explanation. It posits that the reason we've heard nothing, seen nothing, is not because we are alone, but because every civilization in the cosmos is hiding from one another. The universe, in this view, is a vast and dangerous place, where contact with others is a risk too great to bear. To understand the dark forest theory more deeply, we must first consider the implications of intelligence itself. What does it mean for a civilization to be intelligent? How does that intelligence influence how a society interacts with the world around it? On Earth, intelligence has allowed us to build complex societies, develop technologies that alter the fabric of nature, and communicate over vast distances. But intelligence also brings with it the capacity for destruction. We've seen, in our own history, how civilizations have turned on one another, how fear and competition have led to war, suffering, and ultimately, extinction. Now, imagine that fear on a galactic scale, that in the vast, cold expanse of space, every intelligent civilization has developed a survival strategy based on the understanding that contact with another civilization might be the end of them. The dark forest theory suggests that the universe is not a place of peaceful coexistence or collaboration, as we might hope, but rather a battleground of silence, where each civilization is a hunter waiting in the shadows. The logic is simple. Any civilization capable of reaching out across the stars must have the means to destroy others. If a civilization has the power to explore space, it likely has the power to destroy other civilizations that might pose a threat. And so, the only logical strategy for survival is to remain hidden, to say nothing, to do nothing, to ensure that you are never seen. This view of the universe is stark and frightening. It suggests that every intelligent species, from the most advanced to the most primitive, is bound by the same fundamental fear, the fear of being discovered. In a universe where resources are finite and the means to annihilate are ever more advanced, revealing your location or intentions to another civilization could be tantamount to signing your own death sentence. The universe, then, becomes a dark forest, where each civilization hides its presence as best it can, aware that any noise or signal could draw the attention of something far more powerful, something that sees others not as potential allies, but as threats to their own survival. At the heart of the dark forest theory is a disturbing calculation about survival. In this model, every civilization faces an existential dilemma. Do you trust that others will act in good faith? Or do you assume that all others are threats, just waiting for the opportunity to destroy you? The theory operates on the principle of what is known in game theory as the prisoner's dilemma, a concept that explores the tension between cooperation and self-interest. In the case of extraterrestrial civilizations, this dilemma would play out as a question of whether to reveal your presence to others, knowing that doing so might attract the attention of a more advanced and hostile civilization. In the prisoner's dilemma, two players can choose to cooperate or betray one another, with the most beneficial outcome occurring only if both cooperate. However, if one player betrays the other, the betrayer wins, and the betrayed loses. The optimal strategy in such a situation is often betrayal, as it guarantees survival at the expense of the other. In the context of the dark forest theory, the prisoner's dilemma manifests as the choice to either hide your existence or risk being destroyed by a stronger civilization. Just as in the prisoner's dilemma, betraying your own silence and revealing your presence is a gamble, one that could have catastrophic consequences. The universe, in this model, becomes a game of survival, where civilizations are locked in a battle of mutual distrust. Each civilization, aware of its own vulnerability, must assume that every other civilization in the cosmos is equally cautious, equally fearful, and equally capable of turning hostile. This leads to the grim conclusion that the best strategy is simply to remain silent, to ensure that no one knows of your existence, because the alternative, revealing your location or intentions, could be fatal. The dark forest theory also provides a potential solution to another troubling aspect of the Fermi Paradox, the Great Filter. This is the idea that somewhere in the evolutionary history of intelligent civilizations, there is a critical, almost insurmountable obstacle that prevents them from reaching the stage of interstellar communication or exploration. If the dark forest theory holds true, then the Great Filter may not be a single event in the past, such as the emergence of life or the development of complex organisms, but rather a self-imposed filter, the natural consequence of civilizations reaching a certain level of technological advancement and realizing that survival requires isolation. This interpretation of the Great Filter suggests that the filter is not a one-time event that eliminates civilizations early in their development, but rather a constant pressure that keeps civilizations from ever reaching the point where they actively seek contact with others. As civilizations advance, they may discover that their technology has outpaced their ability to trust other beings. Their survival instincts may push them to withdraw into themselves, hiding their presence and avoiding any interaction that might expose them to existential risk. The filter, in this sense, could be the realization of the dark forest, the point at which a civilization recognizes that contact with others is a threat and that survival depends on silence and secrecy. This theory adds an eerie layer of complexity to our understanding of the universe. It suggests that civilizations may be capable of incredible technological feats, space travel, artificial intelligence, and advanced energy manipulation. But the wisdom to understand that these capabilities also bring with them the power to destroy may lead to their isolation. If this is the case, then the reason we haven't detected any alien civilizations may not be because we are too primitive to recognize them, but because they are intentionally hiding from us, just as we would hide from them. One of the most unsettling aspects of the dark forest theory is its psychological and ethical implications. It forces us to confront the possibility that the nature of intelligence itself, the very thing that allows civilizations to rise and thrive, may also be the source of their downfall. Intelligence, in this view, is not a beacon of hope, but a tool of survival that drives civilizations to become increasingly isolated, fearful, and defensive. The implications of this theory extend beyond the question of extraterrestrial life. If the universe is truly a dark forest, where every civilization must hide to survive, then what does this say about us as a species? Are we too on the verge of becoming part of this silent cosmic forest? As humanity continues to advance technologically, the fear of other civilizations and the desire to keep our existence secret may grow stronger. Just as in the dark forest, we could one day find ourselves faced with a decision to reveal our presence to the cosmos or to remain hidden in the shadows. This raises a deeper question about our ethical responsibilities in the search for extraterrestrial intelligence. If we believe that silence is the key to survival, should we be actively seeking out signals from alien civilizations? Or should we be as cautious as they are, hiding our presence from the stars? In a universe that might be teeming with intelligent life, are we making a dangerous gamble by reaching out? Or are we simply following the inevitable path toward cosmic isolation? The dark forest theory also touches on the nature of trust and cooperation. If every civilization is locked in a cycle of distrust, where does that leave us? Can intelligent beings ever learn to trust one another? Or is fear the only constant in the universe? As we ponder these questions, we are left with a disquieting realization. The dark forest theory may not only explain why we haven't found extraterrestrial life, but it may also offer a glimpse into the future of humanity. In a universe filled with dangers and unknowns, survival might depend not on contact, but on silence. A silent, ever-expanding forest where the only rule is to hide. Or is it a sign of something far darker and more dangerous? As we continue to search the stars, our efforts are met with the eerie quiet of space. a silence that grows heavier with each passing year. The possibility that we are not alone is tantalizing, but the prospect that we may be surrounded by civilizations, each one hiding in fear, casts a shadow over our optimism. If the dark forest theory holds, we might be faced with a profound paradox. Are we truly alone, or are we simply too loud, too brash, too eager to reveal our presence to the cosmos? It suggests that our search for extraterrestrial life might not be about finding someone to connect with, but rather about treading carefully, lest we announce our location to those who would see us as a potential threat. The longer we search, the more we might begin to realize that our curiosity is a double-edged sword. While we yearn to know that we are not alone, that there is intelligence beyond our planet, we also risk revealing ourselves to a universe that may be far more dangerous than we can imagine. The act of broadcasting our existence, whether through radio waves, laser signals, or any other form of transmission, could be the very thing that attracts the wrong kind of attention. Just think of how we, as humans, have treated each other throughout history. Empires have risen and fallen, driven by the desire to conquer, expand, and eliminate threats. Civilizations that once coexisted peacefully have often succumbed to the lure of dominance and survival, leading to wars, destructions, and eventual collapses. The fundamental nature of intelligent life is bound by the will to survive, often at any cost. And when that survival is threatened, humans, like other beings, have historically responded with aggression, mistrust, and fear. What if extraterrestrial civilizations are no different? If the universe is truly a dark forest, where each civilization is hidden in the shadows, the psychological toll on those civilizations must be immense. The constant vigilance, the ever-present fear of discovery, would foster a deep sense of isolation. What would it feel like to be an intelligent species, knowing that any outward signal could lead to your extinction? The pressure to remain silent would weigh heavily on every society, making communication, cooperation, or even exploration extremely difficult. In this scenario, isolation is not merely a physical state but a psychological one as well. The act of hiding would not only be a strategy for survival, but a constant mental burden, a fear that exists on an existential level. For how long could any species endure such a condition without suffering from psychological fatigue, alienation, or even eventual collapse? Could the intense isolation experienced by civilizations in this dark forest lead to their ultimate downfall? Perhaps, as the pressure of living in constant fear mounts, societies might turn inward, retreating from the stars, no longer interested in expanding beyond their own planets or even interacting with their own kind. Could this fear drive civilizations to become stagnant, unable to progress, locked in a state of perpetual survival mode? The dark forest theory offers not just a solution to the Fermi Paradox, but also a stark meditation on the nature of intelligence itself. It suggests that, as intelligent species advance, they must grapple with the realization that their own capacity for destruction makes them just as dangerous as the threats they perceive from others. This tension between technological capability and the need for secrecy creates a paradox where civilizations are simultaneously more capable and more vulnerable than ever before. Each civilization becomes a silent observer, too afraid to make a move lest it trigger the inevitable end. One of the more troubling aspects of the dark forest theory is its implications for trust and cooperation. The very nature of intelligence, our ability to understand, adapt, and innovate, seems to come with an inherent flaw: our fear of others. Trust is a cornerstone of any thriving society. It allows us to build relationships, share knowledge, and collaborate for common goals. But in a universe where trust is a liability, cooperation becomes a distant dream. If the theory holds, it means that even the most advanced civilizations, with their immense knowledge and technology, might be locked in a perpetual state of suspicion. No one can afford to trust anyone, because any act of trust could be a fatal mistake. The question becomes, can any civilization ever evolve beyond this fear? If the dark forest is indeed the nature of the universe, then it might be a universal truth that no civilization, no matter how advanced, can escape. Every intelligent being is destined to become a hunter in the dark, forever hiding, forever listening, waiting for others to make a move. This leads us to a haunting realization. If trust is impossible in the cosmic forest, what hope do we have for building meaningful relationships with extraterrestrial life, if and when we do encounter them? Would we be able to see past our own fear and reach out, or would we too become prisoners of our own survival instincts, recoiling in terror at the thought of revealing ourselves? Would we, as a species, fall into the trap of seeing every other civilization as a potential threat, unable to trust anyone but ourselves? This existential question brings us to an ethical crossroads. If the universe is indeed a dark forest, where the safest course is to remain silent, should we continue our search for alien life? Should we persist in sending out signals, hoping to hear back from someone, anyone, out there? Or should we, like the civilizations we seek, hide in silence, protecting ourselves from the dangers that might lie in the depths of space? The search for extraterrestrial life has been a central goal of humanity for decades. SETI, Search for Extraterrestrial Intelligence, has been dedicated to scanning the cosmos for signals that might indicate the presence of alien civilizations. But as the silence stretches on, we are left to wonder, are we broadcasting our presence into a silent and empty void? Or are we sending out signals into a dark, dangerous world where no one dares respond? If the dark forest theory is true, then our very efforts to communicate with the cosmos might be an act of profound risk. The more we reveal ourselves, the more likely it is that we will attract the attention of a civilization that views us as a potential threat. In this light, our search for extraterrestrial life may not only be a scientific endeavor, but a dangerous gamble, one that could result in the worst-case scenario, the discovery of a civilization far more powerful and hostile than our own. If we continue along our path of technological advancement, it's possible that we may one day face the same dilemma that other civilizations have faced, to reveal ourselves or remain hidden. As we develop more powerful technologies, artificial intelligence, quantum communication, advanced space exploration, will we find ourselves on the brink of a cosmic decision? Will we choose to send signals into the stars, reaching out to others? Or will we, like the civilizations before us, retreat into the safety of silence, protecting ourselves from the risks of contact? The dark forest. Theory forces us to confront the future of humanity in a new light. It compels us to ask whether we, too, might one day fall into the same cycle of fear, hiding our existence from the universe in an effort to survive. It raises questions about our responsibility as we advance technologically. Should we seek contact, or is our survival bound to secrecy and silence? And if we do choose to hide, what does that mean for the future of human exploration and growth? Can humanity truly thrive if it is constantly afraid of making its presence known? As we ponder these questions, one thing becomes clear. The silence of the cosmos is not just an enigma, it is a warning. The dark forest is not just a theory, but a metaphor for the existential risks we face as we explore the stars. It challenges us to think deeply about our place in the universe and about the choices we will have to make in the future. In the end, we must ask ourselves, will we step out of the shadows, or will we remain hidden in the dark forest of the unknown, forever alone, forever silent? Picture, if you will, a vast, dark ocean stretching far beyond the horizon. You stand at the edge of an endless shore, the tide pulling away from your feet. Somewhere out there, beneath the waves, lie untold mysteries, islands of potential, remnants of civilizations, perhaps even signs of life that have risen and fallen long before us. The ocean is immense, the stars above a testament to the size of the vast space we occupy. Yet there is something unsettling about this quiet expanse. The ocean is silent. The islands remain hidden, and the search for something beyond seems unfruitful. For every attempt at discovery, the darkness pushes back, revealing only more questions. This is the crux of the Great Filter, a theory that seeks to explain the strange silence of the cosmos, the very same silence we explored earlier in the context of the Fermi Paradox and the dark forest theory. Despite the overwhelming number of stars and planets in the universe that should theoretically support life, we've found no definitive evidence of extraterrestrial civilizations. We hear no voices, see no ships on the horizon. The Great Filter is a theory that aims to explain why, despite the seemingly perfect conditions for life elsewhere in the universe, no other civilizations have made contact, or perhaps why we have not yet reached them. To understand the Great Filter, we must first recognize that it's not a single event, but a series of bottlenecks or obstacles that any civilization must face to survive long enough to explore space, communicate across galaxies, or reach the heights of technological and cultural advancement. The theory suggests that there are significant hurdles in the development of life, and at some point along this path, a civilization, or species, may be doomed to fail, unable to overcome the obstacles that prevent them from reaching a level where they could become aware of or make contact with other civilizations. Perhaps we are just too young, or perhaps we've already passed the filter, leaving other civilizations behind. Either way, the theory invites us to consider the possibility that there are unknown forces, invisible and inevitable, that could keep us from ever becoming part of the galactic community we so desperately seek. The Great Filter is not a recent idea, but rather a reflection of humanity's growing understanding of our own fragility in the cosmos. The search for extraterrestrial life has been a part of human culture for centuries, from ancient astronomers gazing at the stars to modern scientists peering into the depths of space with sophisticated telescopes. The idea that life might exist beyond Earth is as old as civilization itself. Yet, with all our advances, all our technology, we find ourselves staring into an empty sky. The Fermi Paradox asks the question, if life is abundant in the universe, why haven't we found any evidence of it? The Great Filter seeks to answer that by proposing that the reason is not a lack of potential for life, but a fatal barrier that prevents civilizations from reaching the point where they could communicate or be discovered. The theory suggests that the universe may be filled with life, but that most civilizations never survive the bottleneck that leads them to a higher level of development, and thus remain silent, just as we are. But what is this filter? What exactly is preventing us, and possibly every other civilization, from taking that next step? To explore this idea, we must break down the potential stages at which this filter could occur. One of the most discussed possibilities in the search for the Great Filter is the origin of life itself. After all, if life is so rare, maybe the filter exists at the very beginning, during the transition from non-life to life. It's easy to assume that life must be relatively easy to create given the size and scope of the universe, but the reality may be far more complicated. Consider the simple yet profound question: how did life begin on Earth? The answer remains elusive. We know that life on Earth emerged around 3.8 billion years ago, but how it came into being, whether through chemical reactions in the primordial soup or some other process, is still unknown. Scientists have long debated how non-living matter could transform into living organisms, and while there are theories, such as abiogenesis, life arising from inorganic compounds, no one has been able to replicate the process in the laboratory or fully explain how it might have happened. The rarity of life's origins suggests that the Great Filter could exist at this very early stage. If it's incredibly difficult for life to form in the first place, a process that might require very specific conditions and billions of years of precise circumstances, then it's entirely possible that life is much rarer in the universe than we assume. Perhaps most planets simply never make it past this initial hurdle, leaving them barren and devoid of life. If this is the case, Earth may be one of the very few exceptions, making us a rare anomaly in a universe full of dead worlds. If life can arise, then the next potential filter may be the leap from simple, single-celled organisms to more complex life forms. Earth's history shows us how long it took for life to evolve from simple bacteria to the diverse array of complex organisms that exist today. After all, it took over 2 billion years before multicellular life forms appeared, and even longer before the first land-based plants and animals emerged. Complexity, in the biological sense, is rare and difficult to achieve. While simple life might be common, complex life, with its specialized organs, systems, and abilities, is much more challenging. Evolution by natural selection provides a mechanism by which simple organisms can evolve into more complex forms, but it is a slow, uncertain process. The path to intelligence, to self-awareness, to the ability to build technology, is even longer and more improbable. Could the Great Filter be located somewhere along the path of this complexity, where life tends to hit a wall, unable to evolve beyond a certain point? The bottleneck could also be caused by other factors: environmental changes, natural disasters, or cosmic events that decimate a civilization's progress. A world that faces a mass extinction event, such as the asteroid that wiped out the dinosaurs, could suddenly find itself set back millions of years. In this scenario, intelligent life forms that might have emerged during this time never had the chance to evolve. If life does become complex and intelligent, the next critical juncture would be the development of advanced technology and the inevitable risks associated with it. The Great Filter may lie in the transition from a species that can survive in its environment to one that has the power to destroy itself or to destroy others. On Earth, we have witnessed the potential for self-destruction many times. The development of nuclear weapons, for example, has created a situation where humanity could theoretically wipe itself out in a matter of days or hours. The proliferation of these weapons, combined with the power of climate change and other existential threats, creates a precarious balance. It is possible that the Great Filter exists precisely here, in the transition from a species that has mastered the basics of survival to one that has the potential for self-destruction. Many researchers believe that technological civilizations inevitably reach a point where their capabilities outpace their ability to manage the consequences. The more advanced the technology, the greater the risk of catastrophe. This has led to what some call the technological bottleneck, where civilizations are either destroyed by their own inventions or are rendered incapable of advancing further due to environmental collapse or resource depletion. In the case of extraterrestrial civilizations, the Great Filter could be something far more advanced, a technological leap that no civilization can survive. The ability to harness power on a planetary scale, or even to manipulate space and time, could create dangers that are simply too great to overcome. A civilization that reaches this point might self-destruct or become isolated, never advancing to the point where it can explore the stars or communicate across vast distances. One of the most unsettling aspects of the Great Filter theory is the implication it has for humanity's future. If the Great Filter lies ahead of us, meaning that it has yet to happen, then our civilization may face a catastrophe that we are not yet prepared for. The possibilities are chilling. We could encounter a sudden extinction event, an environmental collapse, or some other disaster that we are powerless to stop. The silence of the universe, the lack of evidence of other civilizations, might be a sign that they never made it past the great filter, and that we, too, might not. On the other hand, if the great filter lies behind us, meaning that we have already passed the most difficult stage of survival, then we are among the rare few who have made it through. But even then, the universe remains a treacherous place. The fact that we have survived this far doesn't guarantee that we will continue to thrive. As we continue to advance technologically, the risks we face only increase. The great filter may simply be a looming presence, always one step ahead, ensuring that only a tiny fraction of life forms ever make it to the stars. The great filter theory forces us to confront some of the most difficult questions about our place in the universe. If the universe is teeming with life, why haven't we found anyone else? And if civilizations are out there, what stopped them from making contact? Are we on the verge of discovering that we are part of a very small, select group of survivors? Or are we on the brink of facing a challenge that will prevent us from ever reaching the stars? As we continue to look into the vast expanse of the cosmos, we are left to grapple with the haunting question: are we truly alone? Or are we simply too early, too young, or too fragile to survive long enough to meet the others that may once have existed, or might still exist, out there? The great filter theory forces us to confront a reality that is at once humbling and terrifying. The silence of the universe might not be a reflection of its emptiness, but of its brutal selection process. There's a poignant sense of isolation in the idea that Earth and humanity might be one of the very few civilizations that have made it through the filter. If this theory holds, it means that the vast majority of planets that once might have supported life simply failed to reach the critical junctures that would have allowed them to develop advanced technologies or communicate across the stars. If we are one of the exceptions, it makes our position in the universe all the more extraordinary and all the more fragile. We are not witnessing the bustling activity of other civilizations. We are witnessing the silence that results when life faces immense challenges at every step. The implications of this realization are profound. We might be living in an era where we have already passed through the most dangerous and difficult phases of development. Yet, if that is true, why haven't we made contact with any other civilizations? Why is the galaxy still so eerily quiet? If the great filter is something that has already been overcome by humanity, then we are among an elite few. But that status comes with its own set of questions. Does that make us a cosmic rarity? Or does it simply mean we've been lucky enough to survive what so many others could not? The notion that Earth is one of the few planets to have made it through this filter is both comforting and terrifying. If this is true, it suggests that the odds of intelligent life making it to the stars are astronomically slim. Perhaps the universe is full of planets with microbial life, but complex life that could build technology, explore space, and reach out to others, is exceedingly rare. And if humanity is one of the lucky few to have survived the process, then it means we may be among the last to do so. What is perhaps the most unsettling aspect of the great filter is the possibility that it lies ahead of us. If the great filter is still to come, then humanity's future is far from guaranteed. We could be standing on the precipice of an existential crisis, one that threatens to snuff out our existence before we can spread our reach beyond the confines of Earth. The sheer number of existential risks we face is daunting. Climate change, nuclear conflict, pandemics, resource depletion, and the eventual burnout of our own planet. These challenges could be the very barriers that prevent us from advancing beyond our current technological limitations. Consider the concept of technological escalation. As civilizations grow more technologically advanced, they also grow more powerful and more vulnerable. Technology, while offering immense benefits, also brings with it risks. Our mastery of nuclear energy has given us the power to destroy entire cities, and our control over the environment has contributed to accelerating climate change. As technology progresses, so too does the potential for catastrophic failure. We might be living in an age where the very technologies that have allowed us to thrive, artificial intelligence, genetic engineering, and space exploration, could be the same forces that lead to our undoing. The Great Filter could be lying in wait just beyond the horizon of our technological capabilities. The question becomes, how do we navigate the coming storm? How do we ensure that our species can overcome the challenges ahead without succumbing to self-destruction? This is where the lessons of the past become crucial. The civilizations that failed to survive the filter likely did not recognize the dangers until it was too late. As we advance, we must be mindful of the potential risks our own technology might pose, and we must work collectively to mitigate those dangers. Our survival may depend not on pushing forward with unchecked ambition, but on finding ways to proceed with wisdom and caution. Yet another possibility remains. Perhaps the Great Filter is beyond our current understanding, something so complex or so alien to our way of thinking that we cannot even conceive of it. It could be a technological leap, a cosmic event, or a natural process that is beyond our grasp, something that no civilization has ever been able to navigate successfully. If this is the case, then humanity's fate might already be sealed, regardless of how carefully we tread. Consider the implications of such a scenario. If the filter lies far ahead, it might take the form of a technological development so advanced that it requires us to transcend our physical form or our understanding of the universe itself. In such a case, any civilization that reaches this point might find itself confronted with an obstacle so vast that no amount of scientific inquiry or technological innovation could overcome it. It would be as if the universe has a built-in mechanism to prevent civilizations from becoming truly cosmic in scope, as though there is a limit to how far intelligence can evolve before it must face an inevitable fall. This kind of filter might involve scenarios we can barely imagine. For example, civilizations might eventually develop artificial intelligence that surpasses them in intelligence and capability, leaving humanity, and perhaps every species before us, obsolete. In other words, the ultimate filter might be the rise of a force that cannot be controlled or even understood, one that renders the entire concept of interstellar exploration irrelevant. This could explain the silence of the universe. Intelligent civilizations might evolve and advance only to be replaced by forces beyond their control, forces that either self-destruct or evolve into something incomprehensible, leaving no trace of their existence behind. On the other hand, if the Great Filter lies behind us, it suggests that humanity has already overcome the most difficult and dangerous challenges in the history of life. This would mean that the extraordinary difficulty of evolving from simple, single-celled organisms to a species capable of creating complex technologies and exploring space has already occurred. In this scenario, we might be among the very few life forms in the galaxy that have passed through this gauntlet of survival, and the universe's silence might simply be the result of the fact that most civilizations are still at an earlier stage of development or have failed to survive their own filters. But even in this case, the future of humanity is not guaranteed. The fact that we have made it this far doesn't ensure that we will survive long enough to explore the stars or make contact with other intelligent civilizations. The Great Filter may be a constant presence, lurking just ahead, ensuring that only a tiny fraction of civilizations ever reach the stars. If we are one of the fortunate few, it is only because of a combination of factors: our ability to adapt, our resilience in the face of extinction events, and perhaps a bit of luck. If we have indeed passed the Great Filter, the question then becomes, what does this mean for our future? Do we simply have to outlast the many risks and existential threats that still loom before us? Or is there something more we need to accomplish before we can become true explorers of the cosmos? Perhaps the next step is not to reach out into space, but to solve the problems here on Earth, to ensure that we have the stability and wisdom to survive long enough to evolve further. At the heart of the Great Filter theory is the terrifying realization that the universe might be teeming with life, yet it remains silent because life faces such immense challenges that few civilizations ever make it to the point where they can communicate across galaxies. The silence is not an indication of emptiness, but a reflection of the brutal reality that only a tiny fraction of life forms ever survive long enough to reach the stars. If the Great Filter lies ahead of us, then humanity must tread carefully, as the risks we face could be insurmountable. If the filter is behind us, we must cherish the rare opportunity we have to thrive and reach beyond our planet. Either way, the Great Filter forces us to confront our own fragility in the face of an indifferent, vast, and potentially hostile universe. The silence of the stars is not just a mystery, it is a warning. The Great Filter is a challenge that every civilization must face, and how we navigate it will determine whether we join the ranks of the silent or become one of the rare few that have made it beyond the darkness to explore the cosmos. In the end, the Great Filter is more than a scientific theory. It is a mirror reflecting the most profound existential questions about our place in the universe, our potential for survival, and the uncertain future that lies ahead. As we continue our journey into the stars, we must ask ourselves, will we be the ones to break the silence, or will we too fade into the void, another forgotten civilization in the vast ocean of time? Imagine a scene far beyond the confines of our planet, a vast and infinite cosmos, where stars glitter like distant embers in a boundless sea of dark emptiness. These stars, bright and full of life, burn fiercely for billions of years, illuminating the cold vacuum of space. Some eventually exhaust their fuel and collapse into black holes. Others explode as supernovae, scattering their matter across the universe in a beautiful, chaotic dance. In the dark corners of this cosmic theater, galaxies drift slowly apart, their once vibrant connections slowly stretching, straining, and eventually severing. As you stand in the silent vastness of this universe, one thing becomes painfully clear. Everything, the stars, the planets, the galaxies, and even the black holes, is moving toward an inevitable end. This end, as chilling as it may sound, is not a cataclysmic explosion or fiery destruction. It is, rather, the gradual extinguishing of all energy, a state of complete and irreversible entropy. This is the fate predicted by the heat death of the universe. The concept of heat death is one of the most disquieting yet profound theories about the long-term future of the cosmos. It paints a picture of a universe where, over unimaginable spans of time, everything we know, every star, every planet, every living organism, will gradually fade into nothingness, leaving only a cold, lifeless expanse. There will be no heat, no motion, no energy. Just an eternal, featureless stretch of time where the universe has run its course and every possibility has been extinguished. But how did we arrive at this conclusion? And what does it mean for our understanding of the universe and our place within it? To answer that question, we must first examine the principles of physics that govern the behavior of energy, matter, and time. From there, we will venture into the darker, more speculative realms of this ultimate fate, pondering whether heat death is truly the final word, or if other, even more enigmatic possibilities lurk just beyond our grasp. To understand heat death, we must begin with the laws of thermodynamics, the fundamental rules that govern the flow of energy and the behavior of physical systems. The first law of thermodynamics tells us that energy cannot be created or destroyed. It can only change forms. Energy in the universe is finite, and it can neither be created from nothing nor vanish into nothing. The second law, however, introduces a much more ominous concept: entropy. Entropy can be thought of as the measure of disorder or randomness in a system. In the simplest terms, the second law tells us that the entropy of an isolated system will always increase over time, meaning that systems will tend to evolve toward a state of greater disorder. If you think of the universe as a massive clock, entropy is the inevitable ticking of the hands, moving forward, regardless of whether we are ready or not. In practical terms, entropy suggests that energy in a closed system, such as the universe, will eventually spread out evenly, and as this happens, the capacity of the system to do work will diminish. In other words, the universe will run out of usable energy. Stars will burn through their fuel and die, matter will scatter and become more spread out, and eventually, everything will reach a state of thermodynamic equilibrium, a point where there is no more useful energy left to be extracted, and no more processes that can produce meaningful change. The end result of this process is what we refer to as heat death, a state in which the universe has reached maximum entropy and has become a cold, dark, lifeless void. There will be no more stars, no more planets, no more motion. The fabric of space itself will stretch so thin that it will become almost imperceptible. The universe will be in a state of perfect uniformity, where every particle, every atom, and every piece of matter is spread out and without energy to spare. No heat will remain, no light, no movement. Only the cold, unfeeling vastness of an endless, empty expanse. The timeline of the heat death of the universe is beyond human comprehension. It is not something that will happen in the next few centuries or even millennia. It will take trillions of years, far beyond the span of human civilization or even the lifespan of our sun. In fact, the sun itself is in the middle of its life cycle. It has been burning for about 4.5 billion years and will continue to shine for another 5 billion years before it exhausts its fuel and transforms into a red giant, eventually shedding its outer layers and becoming a white dwarf. But even after the death of our sun, heat death remains a distant theoretical endgame. The universe will continue on for far longer than the Earth, the solar system, or even the stars we know today. This timeline is so incomprehensibly vast that it's difficult for the human mind to fully grasp the implications. But let's try to put it in perspective. After the death of stars like our sun, the remaining remnants, white dwarfs, neutron stars, and black holes, will continue to cool, their energy slowly leaking away into the void. Even the black holes, which have long been regarded as cosmic objects that consume everything in their path, will eventually exhaust their energy. Over vast periods of time, on the order of 10 to the power of 100 years, according to some estimates, even black holes will evaporate via a process known as Hawking radiation. The last remnants of matter and energy will slowly fade away, leaving nothing behind. Once this process is complete, the universe will exist in a state of complete thermodynamic equilibrium. Every atom, every photon, every particle will be spread out evenly across the universe. There will be no structure, no order, and no possibility for life or change. Time itself will continue, but it will be meaningless. There will be no observers to witness it. But even as scientists predict the heat death of the universe, they acknowledge that this theory may not be the absolute end. The fate of the universe, while governed by the laws of physics as we understand them, may still hold mysteries we have yet to uncover. Some theoretical physicists propose that there may be other, unforeseen factors that could alter the course of events. For example, some suggest that dark energy, the mysterious force accelerating the expansion of the universe, could play a larger role in determining the universe's ultimate fate than we currently realize. Dark energy is causing galaxies to move apart at an ever-increasing rate, and in the far future, This accelerated expansion could lead to a scenario in which all matter is so spread out that no interactions can take place at all. This scenario is sometimes called the Big Rip, and it is one of the most unsettling possibilities. If dark energy's effects increase dramatically over time, the very fabric of space-time itself could be torn apart, shattering galaxies, stars, planets, and even atoms. Another speculative idea involves the nature of quantum mechanics and the potential for quantum fluctuations in a universe at maximum entropy. Some theorists propose that these fluctuations could give rise to new universes, new Big Bangs, or even new forms of existence that we cannot currently predict. Could there be a rebound, a kind of cosmic reset, in which the universe regenerates itself in some form? These ideas, though intriguing, remain firmly in the realm of speculation, with no concrete evidence to support them. For now, the heat death remains the most widely accepted end scenario. As we contemplate the idea of heat death, we are inevitably confronted by the philosophical and existential questions it raises. If the universe is destined to die in such a slow, inevitable fashion, what does that say about our own existence? In the grand scheme of things, our brief, fleeting lives seem inconsequential, a momentary flash in the eternal timeline of the cosmos. This realization can be profoundly unsettling. If the universe ends in heat death, a state of perfect, undisturbed equilibrium, then perhaps nothing we do, nothing we build, will matter in the end. The stars will burn out, the galaxies will disperse, and all of the energy we know will be consumed in the gradual dissolution of matter. Our civilization, our achievements, and our legacy will fade into nothingness, as though they never existed at all. Yet, despite the nihilistic implications of heat death, there is a certain strange beauty in its inevitability. It is a reminder of the finite nature of existence. It compels us to ask questions about the meaning of life and the value of our efforts, even in the face of an impersonal and uncaring cosmos. If everything is destined to end, does that make our experiences and our journeys more precious, more significant in their brevity? As we look toward the future, not just of humanity, but of the universe itself, we are left with a sense of awe and mystery. The heat death of the universe may be the most profound and unavoidable end we can imagine, but it is still a theory, an educated prediction based on our current understanding of physics. There are still vast gaps in our knowledge, still untold phenomena that we have yet to comprehend, and the profound mysteries that lie within the cosmos. The potential of the universe is not confined to what we see in the stars or the galaxies. It stretches further into realms beyond our comprehension, where concepts like time, space, and energy could be subject to rules we have yet to understand. At this crossroads of human knowledge and cosmic enigma, one of the most fascinating, though terrifying, prospects is that the universe could be far more complex than the heat-death theory suggests. As we uncover more about the fabric of existence, we may realize that the end of everything, a quiet, lonely universe devoid of energy and motion, might not be as absolute as it seems. Take, for example, the fascinating and enigmatic possibility of cyclic universes. What if the universe does not end in a final, irreversible entropy, but rather goes through an infinite series of big bangs and collapses? Known as the Big Bounce theory, this idea proposes that instead of an eternal descent into stillness, the universe could contract, only to expand again in an endless cycle. Each cycle would allow for the birth of new stars, the formation of new galaxies, and perhaps even the emergence of new forms of life. Such a model suggests that the end of one universe could be the precursor to another, allowing existence to continue infinitely in some form. This theory, however, comes with its own set of challenges. The physics behind such cyclic models is not fully understood, and current evidence from the expanding universe seems to suggest that the cosmos is heading toward an irreversible heat death. But the notion that the universe may be part of an eternal cycle adds an interesting layer to our understanding of its fate. Could it be that we are part of a much larger, timeless pattern of creation and destruction? If so, what does this mean for the meaning of life, for the nature of existence itself? Another intriguing possibility is related to the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. As dark energy continues to push galaxies further and further apart, it raises the question, is there a limit to this expansion, or will it continue indefinitely until the universe reaches a state of absolute isolation? Could dark energy eventually reverse, pulling the universe back together in what some call the Big Crunch? In this scenario, the universe would collapse inward, condensing all its matter and energy into a singular point, possibly leading to the birth of a new universe. The cosmic rebirth theory, inspired by this possibility, suggests that the end of one universe could serve as the catalyst for the creation of another, a new chapter in the universe's endless cycle. While these ideas offer a counterpoint to the finality of heat death, they are still speculative. For now, we are left with an overwhelming sense of uncertainty about the ultimate fate of the cosmos. And while the heat death theory is the most widely accepted explanation, it raises profound philosophical questions that challenge the nature of human existence. If the universe, in its grand expanse, is heading toward an inevitable end, where does that leave us? In this context, the heat death theory also touches on the fragility of human life. We may see ourselves as the pinnacle of intelligence, capable of exploring the stars and unlocking the deepest secrets of nature. Yet, in the grand scheme of the universe, we are but a fleeting moment, a single spark in the eternal darkness. It compels us to examine the purpose of our existence. Is there meaning in a cosmos that will one day fall silent? Are our struggles, triumphs, and endeavors significant, or do they dissolve into the vast, indifferent nothingness that awaits us? In the face of such immense and seemingly inevitable decay, there is an undeniable human urge to search for meaning, to grasp onto some sense of purpose amid the sprawling void. It is this search for meaning that has driven our most profound achievements, from the exploration of space to the creation of art, philosophy, and science. Even though the universe may be on a path to cold emptiness, our ability to find meaning in the here and now remains a defining characteristic of our existence. Perhaps, in the end, it is this very search for meaning, this drive to understand, to experience, to create, that gives our lives value. We may never know for sure what lies ahead in the distant future of the universe. The heat death may come, or perhaps some other unforeseen fate. But in the interim, the journey itself, the exploration of knowledge and existence, is a pursuit that transcends the cold finality of entropy. At its core, the contemplation of the universe's eventual heat death forces us to confront the ephemeral nature of life and the universe. It challenges us to consider our place in the cosmos, not as rulers of an infinite realm, but as humble participants in an ongoing, ever-evolving story. We are but one chapter in the infinite history of the cosmos, and our legacy, whether grand or modest, is defined not by its permanence, but by its meaning and impact in the moment. As we venture deeper into the mysteries of the universe, we may uncover more of its secrets, reveal new laws of physics, and perhaps even discover new dimensions of existence. But whether we succeed in that quest or eventually fade into the vast silence of space, the pursuit of knowledge and meaning will be a journey worth taking. For in the grand tapestry of the cosmos, each moment, no matter how fleeting, is a brushstroke of meaning. The universe is vast, and we are small. Yet in our brief flicker of existence, we have the ability to reflect, to dream, and to seek understanding. Perhaps, in the face of the ultimate heat death, that is the most profound gift of all. For when all is said and done, It may not be the cold, lifeless void that defines the universe, but the warmth of our curiosity and our desire to explore, to make sense of the infinite, even in the face of its eventual silence. So, as we stand on the precipice of the unknown, contemplating the unimaginable scope of time, the vastness of the universe, and the ultimate fate of all existence, let us remember that it is not the final answer that matters most. It is the questions we ask, the discoveries we make, and the lives we lead in pursuit of understanding that shape the story of our place in the cosmos. And in that pursuit, perhaps we can find some sense of peace, knowing that, in our own way, we are part of the eternal dance of the stars. Imagine a world not unlike our own, where every atom, every molecule, every force that governs the universe is delicately balanced, as if perched at the edge of a precipice. The laws of physics we have come to rely on, gravity, electromagnetism, the forces of the atom, all work in a finely tuned harmony. From the grand motion of galaxies to the precise orbits of planets, the universe, as we know it, appears to be stable. But what if, deep within the fabric of reality itself, the universe is far more fragile than we realize? What if the laws of physics, the very foundation of our existence, are not as immutable as we have long believed? What if everything we know could be brought to an end, not by some external force, but from within, by a process we cannot even perceive? This is the haunting possibility presented by the theory of false vacuum decay, a concept so mind-bending that it challenges the very nature of reality itself. According to this theory, our universe might exist in what is called a false vacuum, a state that appears stable but is, in fact, not the true ground state of energy. At any moment, a catastrophic event known as vacuum decay could cause the universe to shift to a lower energy, more stable state, one that is fundamentally incompatible with the laws of physics as we know them. The result would be nothing short of apocalyptic, the sudden, irreversible destruction of the universe as we experience it. But how could something so monumental happen without our knowledge? How could reality itself unravel, leaving us unaware of the impending catastrophe? To understand this terrifying theory, we must first explore the nature of vacuums, the energy states of the universe, and the delicate balance that underpins everything we perceive. When we think of a vacuum, we often imagine a perfect emptiness, an empty space with no matter, no particles, no energy. But in the world of quantum mechanics, a vacuum is far more complex. A vacuum, in this context, is not an empty void, but rather a field of potential, a state of energy. Even in what we consider to be empty space, there are fluctuations at the quantum level, tiny, momentary changes in the energy of the field. These fluctuations are so minuscule that they cannot be detected directly, yet they are the foundation of all reality. At the heart of quantum theory is the concept of vacuum energy, the idea that even the emptiest regions of space are filled with a fluctuating sea of virtual particles. These particles pop in and out of existence, constantly creating and annihilating each other. This is a far cry from the traditional notion of nothingness. Instead, the vacuum is a seething, dynamic field that underlies all of existence. This concept of vacuum energy leads to an unsettling question. What if the vacuum we inhabit is not the lowest possible state of energy? What if it is just one of many potential states, and the true, most stable vacuum is something entirely different, something that, if reached, would fundamentally alter the universe? This is the premise of false vacuum decay. In the theory of false vacuum decay, the universe is assumed to be in a false vacuum state, which means that it is temporarily stable but not in its lowest possible energy configuration. Think of this like a ball sitting in a valley on a hillside. If the ball is in the deepest part of the valley, it is in its true, stable resting state. However, If the ball is sitting on a ledge near the top, it may seem stable, but it is actually in an unstable equilibrium. It is only a matter of time before a small disturbance causes the ball to roll down to the true bottom of the valley, a much lower, more stable point. Similarly, the universe in its current state might appear stable and well-ordered, but it could be teetering on the edge of a much more stable, true vacuum state. The false vacuum we occupy is merely a temporary illusion, one that we cannot detect because we have never experienced the true vacuum. If the universe were to transition from the false vacuum to the true vacuum, the change would be instantaneous and cataclysmic, sweeping across space at the speed of light and destroying everything in its path. This shift could occur at any moment, and we would have no warning. The laws of physics, as we understand them, would break down completely. Gravity, electromagnetism, the strong and weak nuclear forces, all of these fundamental interactions would suddenly become irrelevant as the very structure of space-time is altered. The universe we know would cease to exist, replaced by a fundamentally different reality that we could neither understand nor survive. The idea of vacuum decay is grounded in the field of quantum field theory, which describes how quantum fields behave in space and time. According to this theory, the vacuum is not a uniform, unchanging space, but is instead a fluctuating field that can exist in multiple states. These states are determined by the energy configuration of the field, and the field can decay from one state to another under certain conditions. The process of false vacuum decay begins with a quantum tunneling event, a rare and spontaneous occurrence where the vacuum of space tunnels from the false vacuum state to the true vacuum state. In essence, a bubble of true vacuum would form somewhere in space, and as it expands, it would annihilate everything in its path. This bubble would travel outward at the speed of light, replacing the entire universe with the new, more stable vacuum. The process is so rapid and so all-encompassing that there would be no way for any matter or energy to survive. Once the bubble reaches a region, it would fundamentally alter the structure of space and time itself, leaving behind a void of emptiness. The idea of tunneling between different states of vacuum is a concept borrowed from quantum mechanics, where particles can seemingly leap from one energy state to another, even though classical physics would deem this impossible. In the case of false vacuum decay, this tunneling would cause the fabric of the universe to collapse into a new state, and there would be no way to stop it. The catastrophic nature of the event is further exacerbated by the fact that we are unable to detect or predict when it might occur. The quantum processes that govern these transitions are, by their nature, unpredictable. The timing of false vacuum decay is one of the most chilling aspects of this theory. While it is theoretically possible for the universe to experience a vacuum decay at any moment, the process is so incredibly rare that it might never happen within the lifespan of our sun, or even for billions of years to come. In fact, the chances of this event occurring in the next few million or billion years are infinitesimally small. However, the unpredictability of quantum events means that once the decay begins, it would happen instantaneously and would be utterly irreversible. The death of the universe, if it were to occur through this mechanism, would be a quiet, unseen event. No explosion, no dramatic warning, just the sudden and absolute annihilation of everything we know. The most unsettling aspect of the false vacuum theory is that it's entirely possible that we could live our lives unaware of the catastrophic event that lies just around the corner. If the universe were to suddenly transition to a true vacuum state, we would never know it happened. There would be no time for scientists to detect the event. No warning signs, no gradual changes, just the sudden destruction of the laws of physics. It could happen tomorrow, or it could take billions of years. The worst part is that, given our current understanding, there is nothing we could do to prevent it. Some scientists argue that While the possibility of false vacuum decay is a fascinating theory, it remains highly speculative. The true nature of the vacuum and whether we truly reside in a false vacuum state are still open questions. We simply do not know enough about the fundamental structure of the universe to make definitive predictions about its future. In contemplating false vacuum decay, we are confronted with a question that is as terrifying as it is philosophical. What is the true nature of the universe? Is it really as stable as we think? Or are we living in a fragile, temporary bubble, teetering on the edge of a precipice we cannot see? The idea that the universe itself could change in an instant, without warning, and render everything we know irrelevant, is a sobering thought. As we peer into the mysteries of the cosmos, we are reminded that the universe, for all its beauty and complexity, remains full of unknowns. And some of those unknowns might be far more dangerous than we could ever imagine. Perhaps, as we reach further into the unknown, the question becomes not just why we are here, but how long we can remain before the very fabric of reality itself begins to unravel. Is this a fate written in the stars, or a future we will never see coming? For now, the answer remains hidden in the vast, unexplored reaches of the universe. Imagine a universe where every atom, molecule, and force that governs existence is balanced delicately, as if poised on the edge of a precipice. The laws of physics, gravity, electromagnetism, the forces that bind the atom, all seem to function in perfect harmony, orchestrating the vast dance of stars, planets, and galaxies. The universe feels stable, predictable, as though it has always been this way. But what if the apparent stability of reality is a fragile illusion? What if the laws of physics are not as unchanging as we believe, and lurking beneath the surface of this apparent stability lies a hidden, catastrophic instability? This unsettling possibility is presented by the theory of false vacuum decay, a concept so mind-bending that it challenges our understanding of reality itself. According to this theory, the universe could exist in a false vacuum, a state of energy that appears stable but is not the lowest possible energy state. If the universe were to transition to a true vacuum, the result would be a cataclysmic event that alters the very laws of physics, destroying everything we know in an instant. The universe would cease to exist as we understand it. The laws of physics, the constants of nature, the structure of space-time, everything, all would unravel, leading to an irreversible destruction of the cosmos. But how could this happen without our knowledge? How could reality itself collapse without us ever detecting the shift? To grasp this mind-bending theory, we first need to understand the concept of a vacuum in quantum mechanics. The word vacuum might evoke the idea of an empty, lifeless void, but in the quantum world, it is far more complex. A vacuum is not truly empty, but is instead filled with energy, the energy of fluctuating quantum fields. In quantum theory, even in regions where there is no matter, space is never truly empty. Instead, it is filled with vacuum energy, a fluctuating sea of virtual particles that pop into existence and annihilate each other in a constant dance. This is the true nature of nothingness in the quantum world, a seething, dynamic field of potential where energy and matter constantly fluctuate. Now imagine that the vacuum we experience, the state in which we live, might not be the lowest possible energy state. Instead, it could be a false vacuum, a temporary and unstable state that gives the illusion of stability. In this analogy, think of the universe as a ball sitting on a hillside. It might look stable at the top, but in reality, it is perched on the edge of a much deeper, more stable valley. The ball is poised, ready to roll down into a lower, more stable position. This metaphor applies to the universe. What seems like stability might be an illusion, and the true vacuum state, one of ultimate stability, is just out of reach. If the universe were to transition from this false vacuum to the true vacuum, it would do so in an instant. The transition would occur via a quantum process known as tunneling, an event in which the universe tunnels from one energy state to another, in this case from a false vacuum to a true vacuum. A bubble of true vacuum would form somewhere in space, and as it expands outward at the speed of light, it would destroy everything in its path. This bubble would annihilate all the matter and energy it touches, altering the very fabric of space and time, rendering the universe unrecognizable. Gravity, electromagnetism, and the nuclear forces would cease to exist in their current forms, and everything we know would vanish. The most terrifying aspect of false vacuum decay is that it could happen at any moment, without warning. The universe could be in the process of transitioning to the true vacuum right now, and we would have no way of detecting it. The event would happen so fast that there would be no time for observers to comprehend or react to it. No explosions, no catastrophic warning signs, just a sudden and total shift in the fabric of reality. Our universe as we know it would cease to exist, and everything would be replaced by a completely different set of physical laws. In quantum mechanics, such tunneling events are rare but possible. Particles can jump from one state to another, even if classical physics would deem such transitions impossible. Similarly, the vacuum of space might leap to a lower, more stable state, a shift that could lead to the death of our universe. The process would be so fast and so far-reaching that it would obliterate everything in its path, without even leaving a trace behind. It would be an instantaneous, irreversible event that we could neither foresee nor prevent. While the concept of false vacuum decay may sound like science fiction, it is grounded in the principles of quantum field theory, a well-established area of modern physics. The theory proposes that the vacuum of space is not a uniform, static entity, but instead fluctuates constantly, existing in multiple energy states. When the universe transitions from one state to another, the result can be catastrophic. Timing is one of the most unsettling aspects of this theory. Although the chances of false vacuum decay occurring in the near future are exceedingly small, perhaps requiring billions or even trillions of years, the unpredictability of quantum mechanics means that we can never be certain. The universe might seem stable, but lurking just beneath the surface could be the potential for a quantum shift that would utterly destroy everything we know. The longer the universe remains in a false vacuum, the greater the potential for this transition to occur. However, the exact timing of this event is, as with most quantum processes, completely uncertain. The unpredictability of quantum tunneling adds to the chilling nature of false vacuum decay. It could happen tomorrow, in a billion years, or never at all. The fact that we can't predict when or if it will occur is perhaps the most unsettling aspect of this theory. In a way, the uncertainty of quantum mechanics reflects the ultimate fragility of the universe. While it appears to be stable, it could be teetering on the edge of a profound and irreversible change. But even though false vacuum decay is a fascinating and terrifying concept, many scientists believe that it is purely theoretical at this point. The true nature of the vacuum, and whether we are indeed living in a false vacuum, remains an open question. We simply do not know enough about the fundamental structure of the universe to make definitive predictions about its future. Despite the speculative nature of the false vacuum theory, it raises deeply philosophical questions. What if the universe is not as stable as we think? What if, hidden beneath its surface, there is a deeper reality, one that we are unaware of, and that could change in an instant? The possibility that the universe might unravel, not from some external force but from within, is a sobering thought. As we continue to explore the mysteries of the cosmos, we must acknowledge the potential fragility of our existence. The false vacuum decay theory forces us to confront the idea that the universe could suddenly collapse, leaving us unaware of the impending catastrophe. This unsettling possibility also serves as a reminder that, for all our understanding of the cosmos, there are vast unknowns that could forever alter the course of existence. As we peer into the vast, unexplored reaches of the universe, we are left with the haunting realization that the universe, for all its beauty and complexity, might be far more fragile than we realize. And perhaps, the most terrifying thought of all is that we may never see it coming. Imagine standing at the edge of a quiet, empty space, gazing into the vast expanse of the cosmos. As your eyes drift from one star to another, one planet to another, you begin to realize that you are not alone. In fact, you are not even standing in just one universe. You are in a multiverse. A vast, uncountable number of parallel realities stretch out before you, each with its own history, its own laws of nature, its own version of you. This is the mind-bending proposition of the many worlds interpretation, MWI, one of the most perplexing and controversial theories in modern quantum mechanics. According to this interpretation, every quantum event, no matter how small or seemingly inconsequential, spawns an entirely new universe. Every choice, every decision, every random fluctuation in the quantum world creates a new branch in a tree of infinite possibilities. The universe you know, the one you experience, is just one of an ever-expanding collection of parallel realities, each one a mirror image of your own, but subtly different in its details. As you take in the enormity of this idea, you might begin to wonder, what does this mean for us? Could there be another version of you living a different life, making different choices, following an alternate path? And if this theory is true, then what does it say about the nature of free will, causality, and the very fabric of reality itself? Let's begin by exploring the world of quantum mechanics, the strange and often counterintuitive realm where these ideas take root. From there, we'll venture into the speculative world of the many worlds interpretation, asking questions that have no easy answers, and considering the unsettling possibility that the universe is far more complex than we could have ever imagined. At the heart of the many worlds interpretation is the strange and enigmatic world of quantum mechanics. The quantum world is one that defies our everyday understanding of how things work. At the quantum level, particles exist in a state of uncertainty, neither here nor there, until they are observed. This phenomenon, known as superposition, allows particles to be in multiple states simultaneously. A particle can be both spinning clockwise and counterclockwise at the same time, existing in several possible positions until it is measured. This behavior is most famously illustrated by the thought experiment known as Schrödinger's cat. In this scenario, a cat is placed inside a sealed box with a radioactive atom. If the atom decays, it triggers a mechanism that kills the cat. If the atom doesn't decay, the cat remains alive. According to quantum mechanics, until the box is opened and the cat is observed, it is in a state of both life and death, a superposition of both possibilities. It is only when the cat is observed that the superposition collapses, and the cat is found to be either alive or dead. This paradox raises a crucial question. What happens when a quantum event occurs? How do we go from multiple possible outcomes to a single definite result? In the classical interpretation of quantum mechanics, known as the Copenhagen interpretation, the act of observation causes the wave function to collapse, choosing one outcome over another. But this leaves a troubling question. What does observation mean, and why does it cause the collapse? Is the universe, in a sense, dependent on human observation? And what happens to the other potential outcomes that were not observed? These questions have led some physicists to propose a radical alternative, the many worlds interpretation. The many worlds interpretation was first proposed by physicist Hugh Everett III in 1957. At the time, Everett was attempting to solve the paradoxes of quantum mechanics, particularly the problem of wave function collapse. He proposed that instead of a single collapsed outcome, all possible outcomes of a quantum event actually occur, but in separate parallel universes. Each time a quantum event takes place, the universe splits into multiple realities, each corresponding to one of the possible outcomes. Imagine, for a moment, that you are standing at a crossroads, deciding which path to take. According to the many worlds interpretation, as you make your choice, the universe splits into two. In one universe, you take the left path, and in the other, you take the right. Each version of you lives out the consequences of their respective decisions. Every possible decision, no matter how trivial, gives birth to an entirely new universe. You, the observer, have not chosen just one future. You have created two or more distinct futures, each unfolding independently from one another. In the world of quantum mechanics, this is known as decoherence, the process by which different quantum states evolve separately and do not interfere with each other. While this may sound far-fetched, it offers a solution to the problem of wave function collapse. Instead of the wave function collapsing to one outcome when measured, Everett's interpretation suggests that the wave function simply continues to evolve, creating multiple, non-interfering realities. If the many worlds interpretation is correct, then we are living in a vast, interconnected multiverse, where every decision and every quantum event spawns a new reality. This universe, the one we perceive with our senses, is just one of many in an endless array of possibilities. In some of these alternate universes, you may have made different decisions you didn't even know were possible. Perhaps you never chose to follow a particular career, or maybe you made a different choice in a critical moment of your life. In some parallel world, the you who didn't take the left path is living a completely different existence, following an entirely different course. The idea of parallel universes, where every possible outcome occurs, raises profound questions about the nature of identity and free will. If there are infinite versions of you, each living out a different reality, does that diminish the significance of the choices you make in this world? Are we merely participants in a never-ending game of quantum chance, with every outcome already played out in some alternate dimension? If every possible decision creates a new universe, is free will an illusion, or is it a fundamental part of the structure of the multiverse? Furthermore, if the many worlds interpretation is true, what does it say about the nature of existence itself? Are we merely one version of a vast ensemble of parallel realities, each as real and as valid as the next? Could there be universes where history unfolded in radically different ways? What if, in one reality, the course of human civilization took a completely different direction, or the laws of physics operated in ways we cannot even imagine? These are the kinds of questions that the many worlds interpretation invites us to ask. It stretches the boundaries of what we think is possible and challenges us to reconsider the very nature of reality. Despite its fascinating implications, the many worlds interpretation is not without its critics. One of the biggest challenges to the theory is the lack of direct evidence. Because the parallel universes created by quantum events do not interact with each other, we have no way to observe or measure them. They exist, but they are hidden from our view, and may forever remain beyond our reach. This raises a central philosophical question. If these parallel universes exist, but we can never detect them, do they truly matter? Some physicists argue that the theory is a mere mathematical abstraction, a convenient way to solve the mysteries of quantum mechanics without requiring the collapse of the wave function. Others suggest that the many worlds interpretation is an elegant solution to the paradoxes of quantum mechanics, but one that remains speculative until proven. As we explore the depths of the multiverse, we are left with a sense of wonder and awe. What if the universe we see is only a fraction of a much greater reality? What if our entire existence is just one tiny piece of an infinitely larger puzzle? And most tantalizing of all, What if there are infinite versions of you, each living out an alternate reality, shaped by the choices you make, and the ones you didn't? As the field of quantum mechanics continues to evolve, the many worlds interpretation remains a tantalizing, elusive theory, one that invites us to ask questions about the very nature of existence, choice, and reality. Is this the key to understanding the true structure of the cosmos, or is it simply a thought experiment that stretches the imagination without providing concrete answers? The mysteries of the multiverse remain unsolved, and as we peer deeper into the quantum world, the question of how many worlds exist and how they connect continues to haunt the minds of scientists and philosophers alike. Perhaps, as we uncover more about the universe, we may discover the truth about the parallel realities that lie just beyond our reach. Or perhaps we may find that the mysteries of the many worlds interpretation are just another piece of the puzzle, waiting to be understood. Imagine standing on the edge of an empty, quiet space, gazing out into the vast expanse of the cosmos. As you look from one star to another, one planet to the next, a thought begins to creep in. Perhaps you are not alone in this universe. In fact, maybe you are not even in just one universe. Perhaps you are in a multiverse, a realm where countless parallel realities stretch out before you, each one with its own history, its own laws of nature, and its own version of you. This is the mind-bending proposition of the many worlds interpretation, MWI, one of the most perplexing and controversial theories in modern quantum mechanics. At the core of this idea is a radically different view of quantum mechanics. According to MWI, every quantum event, no matter how small or seemingly insignificant, spawns an entirely new universe. Every choice you make, every decision, and every random fluctuation in the quantum world creates a new branch in an infinite tree of possibilities. The universe you know, the one you experience daily, is just one of an ever-expanding collection of parallel realities, each a mirror image of your own, but subtly different in its details. As you process the enormity of this idea, you may start to wonder, could there be another version of you somewhere, living a different life, making different choices, following an alternate path? And if this theory is correct, then what does it mean for our understanding of free will, causality, and the very nature of existence itself? To answer these questions, we must first dive into the strange, perplexing world of quantum mechanics, the realm of physics that underpins MWI. In the quantum world, particles behave in ways that defy our everyday understanding of reality. At the quantum level, particles can exist in multiple states at once, a phenomenon known as superposition. This means that a particle can be both spinning clockwise and counterclockwise simultaneously, existing in several possible positions until it is observed. One of the most famous illustrations of this is Schrödinger's cat. In this thought experiment, a cat is placed in a sealed box with a radioactive atom. If the atom decays, the cat dies. If it does not decay, the cat remains alive. According to quantum mechanics, until the box is opened and the cat is observed, it is in a state of both life and death, a superposition of both possibilities. The act of observation causes the wave function to collapse, and the cat is found to be either alive or dead. This paradox raises an essential question. What happens when a quantum event occurs? How do we go from multiple possibilities to a single definite outcome? In the Copenhagen interpretation, the standard view of quantum mechanics, the act of observation forces the wave function to collapse and choose a single outcome. But this leads to an unsettling question. What does observation really mean? Why does it cause the collapse of the wave function? Does the universe depend on our observation? And what happens to the other potential outcomes that we didn't observe? These questions have led some physicists to propose an alternative explanation: the many worlds interpretation. First proposed by physicist Hugh Everett III in 1957, MWI suggests that, instead of one collapsed outcome, all possible outcomes of a quantum event actually occur, but in separate parallel universes. Each time a quantum event occurs, the universe splits into multiple realities, each corresponding to one of the possible outcomes. Imagine you are standing at a crossroads, deciding which path to take. According to MWI, as soon as you make your choice, the universe splits into two. In one universe, you take the left path, and in the other, you take the right. Each version of you then lives out the consequences of their respective choices. In this framework, every decision, no matter how small or seemingly insignificant, gives birth to an entirely new universe. The universe you live in is just one of many, and in some of these parallel worlds, you may have made different decisions, taken different paths, leading to entirely different realities. This idea is known as decoherence, the process by which different quantum states evolve independently of each other and no longer interfere. Rather than the wave function collapsing to one outcome when measured, Everett's interpretation suggests that the wave function continues to evolve, creating multiple, non-interfering realities, each one as real as the last. If the many worlds interpretation is correct, then we live in an infinite multiverse, where every quantum event and every decision spawns new realities. In some of these parallel universes, you may have chosen a different career, made different choices in your relationships, or taken an entirely different path in life. In one world, perhaps you didn't choose the left path, and your life followed a completely different trajectory. There are endless possibilities, each one a distinct universe, all existing simultaneously. This raises profound questions about free will and the nature of identity. If there are infinite versions of you, each living out a different reality, does that make your choices less significant? Are you simply one participant in an endless series of quantum events, each playing out in a separate universe? If every possible outcome creates a new reality, does free will lose its meaning, or does it simply become part of the vast structure of the multiverse? Furthermore, if MWI holds true, what does it say about the nature of existence itself? Are we just one version of an infinite set of parallel realities, each as real and valid as the next? Could there be universes where history unfolded in entirely different ways, where the laws of physics are fundamentally different from our own? In one universe, perhaps human civilization developed entirely differently, or in another, the fundamental constants of nature operated in ways that are beyond our comprehension. The implications of the many worlds interpretation stretch far beyond science. They raise deep philosophical questions about the nature of life, identity, and reality. If we truly live in a multiverse, what does it mean to be human? Are we just one small, transient piece of an infinitely larger puzzle? What if the choices we make are not unique, but rather part of an ongoing series of quantum events that unfold across an infinite number of parallel worlds? Despite the fascinating implications of MWI, the theory is not without its critics. One of the biggest challenges it faces is the lack of direct evidence. Since the parallel universes created by quantum events do not interact with each other, we have no way to observe or measure them. They exist, but remain hidden from our view, possibly forever beyond our reach. This raises a fundamental philosophical question. If these parallel universes exist, but we can never detect them, do they truly matter? Some physicists argue that the many worlds interpretation is nothing more than a mathematical abstraction, a way to resolve the paradoxes of quantum mechanics without needing to collapse the wave function. Others suggest that MWI provides a more elegant solution to quantum mechanics, but one that remains speculative and unproven. As we continue to explore the mysteries of the quantum world, the multiverse remains a tantalizing, elusive idea. Could the universe we see be just a tiny fraction of a much larger, more complex reality? Could we be one version of an infinite number of possibilities, each version of us shaped by the choices we made or the ones we didn't? As we peer deeper into the quantum realm, the question of how many worlds exist and how they are connected continues to provoke awe and curiosity. Perhaps one day, the mysteries of the many worlds interpretation will be uncovered, revealing the true nature of existence. Or perhaps we may find that this theory is just one more puzzle piece in the ever-expanding picture of reality, waiting for us to understand. Until then, the multiverse remains a theory, an enigma that challenges our very concept of reality, free will, and the infinite possibilities that lie just beyond our reach. Imagine standing on a darkened beach at night, the waves of the ocean lapping gently at your feet. Above you, the sky is a canvas of twinkling stars, each one a distant sun, a burning ball of energy far beyond your reach. As you look up, you might marvel at the enormity of the universe, the vastness of space, the infinite number of galaxies, stars, and planets that stretch far beyond your comprehension. The sheer scale of it all can be humbling, almost dizzying. And yet, despite this grand, outward expanse, there's a curious question that seems to echo in the back of your mind. How do I know this reality is real? What if, just as you look up at the stars, the entire cosmos, everything you perceive around you, was not as it seems? What if the universe you think you are experiencing is simply a projection, a three-dimensional image cast by a process so sophisticated, so intricate, that you cannot detect it with your senses? What if the universe, the very fabric of existence, is an illusion, a hologram, projected from the farthest reaches of reality? This is the premise of the holographic universe theory, one of the most mind-bending and unsettling ideas in modern physics. According to this theory, the entire universe, including space and time, is not real in the conventional sense. Instead, it is a hologram, a two-dimensional information structure projected into three-dimensional space. In other words, the universe as we perceive it, a vast, solid, three-dimensional world, could be an elaborate illusion, a hologram generated by information encoded on the boundaries of space-time. This idea challenges everything we know about reality, prompting a re-evaluation of the very nature of existence. If our universe is a hologram, what does that say about the nature of consciousness, the mind, and the boundaries of the physical world? Could our perceptions be nothing more than sophisticated tricks of the light, our senses deceiving us into believing we are living in a tangible, real world? And if the universe is a projection, what lies beyond the veil of this hologram? To understand the implications of the holographic universe theory, we must first delve into the foundations of modern physics, where quantum mechanics and the theory of relativity collide, and explore how this theory emerged from the most abstract regions of theoretical physics. The idea that the universe might not be what it seems has a long and winding history, rooted in the deepest corners of theoretical physics. It all begins with the realization that space and time, as we perceive them, are not as solid and fundamental as we once believed. One of the key breakthroughs that paved the way for the holographic universe theory came with the work of physicist Juan Maldacena in 1997. While investigating black holes and quantum gravity, Maldacena proposed a revolutionary idea. He suggested that a particular type of string theory, a theory that attempts to unify all the fundamental forces of nature, might allow us to describe a higher dimensional space-time in a way that didn't require all dimensions to be directly observable. This was a radical shift in thinking. Instead of thinking of space as being made of a continuous expanse, Maldacena's work suggested that the universe might be a projection of information encoded on a lower dimensional surface. His theory proposed that the events inside a black hole could be described by a kind of hologram on the surface of the event horizon, the boundary beyond which nothing, not even light, can escape. For years, scientists had struggled to reconcile the strange world of quantum mechanics with the gravitational forces described by Einstein's general theory of relativity. In the traditional view, space and time were thought to be solid, immutable, with matter and energy interacting through these fixed dimensions. But Maldaceno's proposal that the universe could be described by information encoded on a distant, two-dimensional surface opened up a completely new way of thinking about the nature of reality. It suggested that what we perceive as a three-dimensional world could be nothing more than a projection of information in a lower dimensional space. This idea was deeply unsettling. If the universe is a hologram, it implies that everything we experience, every atom, every galaxy, every star, every person, is simply an image or illusion cast by an underlying code or set of instructions. But how could this be possible? And if our perceptions are nothing more than projections, then what is the nature of the reality behind the hologram? To understand how the holographic universe could work, it's essential to explore some of the mathematical concepts behind it. At the heart of the holographic universe theory lies the notion that the information about the universe, rather than being distributed throughout three-dimensional space, is encoded on a two-dimensional surface, much like a hologram. This surface can be thought of as a kind of boundary beyond which we cannot peer. In Maldaceno's original work, the hologram he proposed was associated with the event horizon of a black hole, the point of no return beyond which nothing can escape. The event horizon, according to classical physics, marks the boundary between what is inside the black hole and what remains outside. But in the holographic view, the event horizon is not just a boundary. It's the place where the fundamental information about the black hole, and potentially the entire universe, is encoded. This is where things get truly strange. The mathematics of holography suggest that all the information within a black hole, which seems to be contained in a three-dimensional space, can actually be described by two-dimensional information on the event horizon. This insight was profoundly important because it suggested that the three-dimensional reality we experience might also be a projection of a two-dimensional surface, just as the image of a hologram seems to emerge from a flat surface, yet gives the illusion of three-dimensional depth. One of the most compelling aspects of the holographic universe theory is that it doesn't simply discard the idea of the universe as a physical reality. Rather, it suggests that reality, as we perceive it, is the result of a complex interaction between information and the way it is encoded in higher dimensional spaces. The universe might seem solid and real, but at its core, it is information, encoded, projected, and rendered in a way that creates the illusion of a physical world. The holographic universe. Theory is deeply connected to another mind-bending concept in quantum physics: quantum entanglement. In a quantum entangled system, the properties of particles become linked in such a way that changing the state of one particle instantly affects the other, regardless of the distance between them. This phenomenon seems to defy the classical understanding of space and time, suggesting that information can be transmitted instantaneously across vast distances. The connection between quantum entanglement and the holographic universe theory lies in the idea that the universe is, at its core, a vast network of interconnected information. In the holographic view, entangled particles are not just linked in space, they are reflections of the same underlying reality, encoded and projected across different regions of the universe. This interconnectedness hints at a deeper, unified structure of reality, one that transcends the traditional laws of physics. Entanglement suggests that the universe is not as it seems. The boundaries between objects, space, and time might be far more fluid and interconnected than we can perceive. The holographic theory takes this one step further by suggesting that the entire universe itself might be a projection of this underlying web of information. Every event, every interaction, every observation might simply be a reading of this encoded data, interpreted by our minds as solid, three-dimensional experiences. One of the most fascinating and unsettling questions raised by the holographic universe theory is the role of consciousness in creating our perception of reality. If the universe is a projection, then who, or what, is observing the projection? Is consciousness the key to perceiving the hologram, or does it play an active role in creating it? In many ways, this question mirrors one of the most profound mysteries in philosophy: the nature of perception. If reality is an illusion, then how do we come to perceive it? What does it mean for the mind to interpret this information? And how do we experience a three-dimensional world if it's nothing more than a projection of two-dimensional data? These questions blur the lines between physics, metaphysics, and consciousness studies, suggesting that the very nature of reality might be far more intricate than we can comprehend. This connection between consciousness and the holographic universe has led some to speculate that the mind itself might be a part of the holographic process. Just as a hologram cannot exist without the light that illuminates it, could consciousness be the fundamental light that brings the universe into focus? Could the mind be both the observer and the creator of the projection? And if so, what does that say about the power of consciousness in shaping our perception of the world? The holographic universe theory, if true, has profound philosophical implications. It challenges our most basic assumptions about the nature of reality, space, and time. If the universe is a projection, then what is the nature of the real world behind it? What lies beyond the boundaries of the hologram, and can we ever know it? It also raises important questions about our place in the universe. If the universe is a hologram, then what does that say about the importance of our experiences, our choices, and our existence? Are we just passive observers in an illusion, or do we play an active role in shaping the universe? And if our perceptions are deceived, then what does it mean to know? Imagine standing on a darkened beach at night, the waves gently lapping at your feet. Above you, the sky stretches out as a vast, twinkling canvas of stars, each one a distant sun burning with energy far beyond your reach. As your gaze wanders across the endless expanse, you feel a deep sense of awe at the immensity of it all. The galaxies, the stars, the planets, all scattered across space in an unimaginable pattern. It's overwhelming, humbling, even dizzying. Yet, as you stand there, lost in the majesty of the cosmos, a thought quietly whispers in your mind. How do I know this reality is real? What if, just as you look up at the stars, everything around you, the entire universe, wasn't as it seemed? What if the reality you perceive is not truly real, but instead an illusion? An elaborate three-dimensional projection cast by a process so sophisticated that you cannot detect it with your senses? What if space, time, and all the matter in the universe were not tangible, but part of a hologram, a complex image projected from a higher dimension? This is the basis of the holographic universe theory, one of the most mind-bending and disorienting ideas in modern physics. According to this theory, the entire universe we experience, with its three-dimensional space, time, and physical laws, is not real in the conventional sense. Instead, it could be a hologram, a two-dimensional information structure projected into three-dimensional space. Essentially, the universe we see, feel, and touch might be an illusion, an image generated by information encoded on the boundaries of space-time. The idea that our reality might be a hologram challenges everything we know about the universe, forcing us to rethink the very nature of existence itself. If the universe is a hologram, then what does that mean for consciousness, for the mind, or for our understanding of the physical world? Could it be that our perceptions, our experiences of the world around us, are nothing more than highly sophisticated tricks of light, constructed by an underlying process beyond our comprehension? And if the universe is a projection, what exists beyond the veil of this illusion? To understand the implications of the holographic universe theory, we must first dive into the foundations of modern physics, where quantum mechanics and the theory of relativity collide, and explore how this theory emerged from the deep corners of theoretical physics. The idea that the universe may not be what it seems goes back several decades, rooted in complex theories and abstract concepts. It all began when physicists started to recognize that space and time, which once appeared as solid, unchanging entities, were actually much more fluid and complex than previously thought. The breakthrough that ultimately paved the way for the holographic universe theory came in 1997 with the work of physicist Juan Maldacena. While studying black holes and quantum gravity, Maldacena proposed an astonishing idea. Certain kinds of string theory, an effort to unify the fundamental forces of nature, could describe a higher dimensional space-time without all dimensions being directly observable. Instead, he suggested, the universe might be a projection of information encoded on a lower dimensional surface. Maldacena's proposal fundamentally shifted how scientists thought about space and reality. Instead of seeing space as a continuous, three-dimensional expanse, his theory hinted that the universe could be described by information encoded on a two-dimensional surface, much like the image of a hologram. This was an extraordinary and unsettling revelation. What we perceive as a three-dimensional world could be nothing more than a projection from a lower dimensional space. But how could this be possible? The implications of this theory are profound, suggesting that everything we experience, from the stars in the sky to the matter around us, could simply be a projection, an illusion, cast by a fundamental code or structure that we can't directly perceive. One of the key concepts behind the holographic universe theory is that all the information about our universe, instead of being spread across three-dimensional space, could be encoded on a two-dimensional surface, similar to how a hologram encodes three-dimensional information on a flat surface. This boundary is the place where all information about the universe is encoded, even though we cannot directly observe it. Maldacena's original work focused on the event horizon of a black hole, the boundary beyond which nothing, neither matter nor light, can escape. In classical physics, the event horizon is simply the point of no return. But in the holographic view, this event horizon becomes more than just a boundary. It becomes the place where the fundamental information about the black hole, and potentially the entire universe, is encoded. The hologram projected from this surface would be an accurate representation of what we perceive as a three-dimensional universe. This insight into black holes led scientists to explore the possibility that the universe itself could work in a similar way. If a black hole can have a holographic description at its event horizon, then why couldn't the universe, as a whole, be understood as a hologram projected from a lower dimensional surface? At the core of the holographic universe theory lies the idea that the universe, instead of being solid and tangible, is essentially a projection, created by the encoding of information from a distant two-dimensional surface. Reality as we know it, therefore, might be a complex interaction of this encoded information, projected into our perception of three-dimensional space. This theory also connects to another fascinating concept in quantum physics: quantum entanglement. In quantum mechanics, particles can become entangled, meaning the state of one particle is directly linked to the state of another, even if they are separated by vast distances. This phenomenon suggests that information can be transmitted instantaneously across space, defying our classical understanding of space-time. In the holographic view, quantum entanglement hints that the universe is not just a collection of isolated objects, but rather a vast network of interconnected information. Entangled particles are reflections of the same underlying reality, encoded and projected across different parts of the universe. This interconnectedness suggests that our perception of separate, independent objects might be an illusion, with the true nature of reality being far more fluid and interdependent. One of the most unsettling aspects of the holographic universe theory is the role of consciousness. If the universe is a projection, then who or what is observing the projection? Could consciousness itself be the key to perceiving the hologram? And if it is, does this mean that the mind plays an active role in creating our perception of reality? This question echoes one of the most profound mysteries in philosophy. What is the nature of perception? If reality is merely an illusion, how do we come to experience it? What role does the mind play in interpreting this information? And how do we experience a three-dimensional world if it is nothing more than a projection of two-dimensional data? Some theorists suggest that consciousness itself could be part of the holographic process, much like light illuminates a hologram. In this view, the mind could be both the observer and the creator of the projection, shaping the reality we experience. If this is true, it suggests that consciousness has a much more active role in the formation of reality than we ever imagined. The implications of the holographic universe theory are not only scientific but also philosophical. It forces us to reconsider our most fundamental assumptions about reality, space, time, and the nature of existence. If the universe is a projection, then what is the real world behind it? What lies beyond the boundaries of this hologram? Can we ever know it? This theory also raises important questions about the significance of our experiences. If everything we perceive is an illusion, then what does that say about our choices, our relationships, our very existence? Are we merely passive observers in a grand cosmic illusion, or do we play an active role in shaping the universe around us? The holographic universe theory offers no easy answers, but it invites us to see the world in a new light. If we are living in a hologram, then the question isn't just how the universe works, but what lies beyond the illusion, and how much of what we perceive is truly real. It challenges us to reconsider the boundaries of reality and the nature of the mind, opening a door to mysteries that may lie just beyond our understanding.